Hello, hi everyone. And now we will start the vision, sensing, and mapping one section. And the first work to present is DA-SLAM, Deep Active SLAM, based on deep reinforcement learning, presented by Martin Alcalde. And Martin, you have 10 minutes, and it's you.
Okay. It says that I can't share screen. Now I can. Thank you. I'm sorry. Hello, everyone. I will very quickly present our work. SLAM is about incrementally building the map of a previously unseen environment, while at the same time locating the robot in it. SLAM has two variants, passive SLAM and active SLAM. In active SLAM, there is a module that can change the robot path in order to get more information about the environment. In the picture, you can see one of the maps that we have used. The tiny black thing here is the robot. I wanted to place this map here this environment really, just to make sure that we are all thinking about the same as the presentation goes on. The objective of this work was to enhance the state-of-the-art algorithms using reinforcement learning for the Deep Active SLAM module. Now, Deep Active SLAM solution. We developed two different agents. So we're using reinforcement learning, so we have two different reward functions. The left one, we call it MC, which stands for map completeness. And the right one is UB, which stands for uncertainty base. Airsul crash, it's minus 100. Then we have C sub t, which stands for the map completeness at the time t. C sub t minus 1 stands for the map completeness at the time t minus 1. Then here we have 1 plus the hyperbolic tangent of a scalar divided a function of sigma, and that function of sigma is called the optimal criterion, which we have referenced in our paper. Then the observation space. For the reinforcement learning module, we only relied on 5 sensors, the 2 on the sides, then 45 degrees and another on the front. So we have that observation vector with 5 elements, and we had to normalize that vector because, yeah, it was very important for the training. Then we have a discrete action space that is very simple. We have forward, turn left, or turn right. Then the state space, the agent selects actions based on the information contained within the state vector S sub t at the time t. So the state vector has 3 different elements. One is the observation at the time t, the previous action, and the previous reward. Then for the general architecture, for the simulation, we have ROS and gazebo. Within that simulation, life cycle is our controller, which takes care of the robot control, path, and communication with G-mapping, which is a lightweight SLAM algorithm running on the background. Also, the controller communicates with the reinforcement learning module. The reinforcement learning module is composed of 3 layers. The first layer is related with the robot environment. Second is related with the reinforcement learning task. And third is the actual implementation of the algorithm. In this case, proximal policy optimization, which was provided by Stable Baselines 3. That is a repository of very well implemented and open source reinforcement learning algorithms. Now, the environment setup. We use ROS, which is Robot Operating System, version Noetic Ninjamis, and for the 3D simulation environment, we use Gazebo, and the robot was Robotic Turtlebot 3 Burger, which has a 360 laser range scanner, that's the LiDAR, and wheel telemetry. The LiDAR range is between 0.12 and 3.5 meters. Now, the environments. We only train on the environment number one, but we did testing in all of them, these four. Um, an important comment is on that environment 3 and environment 4 are on the complex side because they have like some characteristics that make them so, like they have high symmetry, the dense rooms, things that make them the state-of-the-art reinforcement learning active SLAM algorithms struggle with. So that's why we include them. Now I will show you a demo video. Here we have 4 different agents that we developed. The 2 on the right are the ones that use reinforcement learning. Here I have a note, and is that these 2 agents, the reinforcement learning, are going a bit slower because we wrote them on virtual machines. So with the recording software and everything that's going on, they get a bit laggy, but it only affects the simulation speed, so the results should be the same. On here on the left, we have the frontier, which is an active SLAM agent that uses the frontier exploration that we have a reference is in our paper. And here we have an advanced active SLAM agent that we develop that we call YALC, that stands for exploration and loop closing, that uses for exploration the frontier exploration, and for loop closing another work that is referenced in our paper. We can see that frontier just ended, and yeah, the mapping didn't well like 100%, but almost. Completeness is about to end, and you can see that the path is much more smoother than the frontier, and it just ended. And the uncertainty is about to end. And you can see that the path is also very smooth, but here it has like a loop close. So if you compare these 2 maps, this is much better than on the mapping because you can see that the map is much more straight. It has straight line here. It doesn't, has these kind of things here. And YALC, it's revisiting already visited places in order to reduce the uncertainty. Now, I will show a table of different results we have. I have just show the environment too, because it's a small environment and we can see all the episode end. But here I highlighted some results on the third environment that I think that as it's a more complex and bigger environment, it makes more explicit the difference between the agent. First of all, I want to comment that we almost did 100% completeness in every map for every agent. That's very good. Then if we focus on the path length, you can see that in the completeness spaces, the path length is the shortest of all, and the uncertainty base is its longest. The same stands for the time, but for the uncertainty is different. The uncertainty-based agent had a lower uncertainty. Now, the conclusions. Both deep reinforcement learning agents show performance comparable or even better than YALC, which is an advanced active SLAM agent. Also, very good performance or better compared to the state-of-the-art reinforcement learning agents. And also both agents show the ability to transfer acquired knowledge to previously unseen maps, which is a key requirement of SLAM. Now, for the future work, one important thing will be to create an agent that aggregates the 2 proposed one, that meaning seeking to obtain good map while at the same time obtaining shorter paths. Another very good thing will be retraining on complex environments because we just train on the first one and we maybe get like overfit to that one, and yeah, getting like different features extracted for complex maps will be great. Also, testing on real environments will be great because we didn't do so, but we do all the testing on Gazebo, which is a very good simulation. So I think that's it. Thank you, everyone. I think that we'll now jump to the questions section.
Thank you, Martin. Thank you for your presentation. You have some question? Martin, we have a question.
Yeah.
Hello.
Hello.
Hello, Martin. Bruno here from the University of Lars.
I can barely hear you.
Thank you very much for your presentation. Congratulations.
Thank you.
So, Martin, I was wondering if you're going to what is your method?
I'm sorry, I can't hear you.
Can you hear Bruno?
No.
No?
Hello?
Just a second, Martin.
Yeah.
Hi, Martin. Can you hear me?
Yeah, I can hear you now.
Okay. So I was asking if you are going to use your system, your method in real with real robots in real environments. Can you use all the data, all your the knowledge you acquired with simulated experiments? Thank you.
I haven't do so, but from what I hear from different sources, yeah, it can be easily port to like a real environment. Also, as we use the same data for the training and for the inference, you will not have to provide like any extra information to the robot. So yes.
Excellent.
Thank you.
Thank you.
And we have more questions. Question. I have one, Martin. In your proposed method, you trained your agents using only one environment. It's okay?
Yes.
Yes. Why not train in different environments? You have 4 environments, right?
Yeah, because we spend a lot of time trying to make the agent converge, and also we had another problem that we couldn't like make the simulation go faster than 1x. I mean, we could get like to 3x, 4x, but the problem with that is that for some reason we will get like less time steps for episode. So at the end will be the same or even worse. So the problem that we have is that we will spend a lot of time training, like days. So that's why we didn't. I mean, we did some experiments, like train on the first one and then like do a small training on other one, but it was like so small training that I think that I can't see like any improvements. So that's why we decided not to do that. But it was mostly like a time constraint. I think that it will improve a lot the agents to do that.
Nice, nice. Thank you, Martin. Thank you for your presentation.
Yeah, thank you.
Now we will proceed for the next paper. The title is Comparison of the YOLO V3 and SSD models using the balanced dataset with data augmentation and for object recognition in images. This paper will be presented by Daniel Gamar. Daniel, it's with you.
Thank you. Good morning, everybody. My name is. Thank you.
I'm going to text. Okay. Okay, let's look class. Okay, good morning, everybody, once again. My name is Fernando Gamarra. I'm Federal University of Santa Maria, and I'm going to present a paper comparison of the Euro V3 and SSD models using a balanced dataset with data limitation for object recognition in English. This paper is a result of the undergraduate thesis work of Adriana Rios, and it's co-author also for Anselmo Cupra, Fernando Gamarra, all of them from the Federal University of Santa Maria in Rio Grande do Sul, and Marco Quadros from the Federal Institute of Espírito Santo. I don't know if I have. Okay. So the outline of the presentation, we will have an introduction. We will talk about the YOLO algorithm. Also, we will talk about the SSD algorithm, the software architecture, the methodology, the results, and the conclusions. So this article proposes to use the YOLO algorithm, YOLO algorithm version 3, and the SSD algorithm for object recognition. These algorithms would be used in a mobile robot navigation dataset, and also we will apply the data augmentation technique in order to compare these object detection algorithms. So first of all, we will talk about the YOLO architecture. The YOLO algorithm is an algorithm for object detection that uses convolutional neural networks. It has convolutional neural networks, a fully connected layers, and a filter in the output of the algorithm. So how this algorithm works? This algorithm divides the input image in a set of grid cells. I mean, these grid cells simultaneously are applied bounding boxes, and if every bounding boxes is established a confidence parameter, and simultaneously is constructed a class probability map. From these ones and the output, we have a function classifying these bounding boxes with relation to the objects that are in the input image. For experiments, as we have used the YOLO V3 algorithm, it was through the Darknet 53. Darknet 53 is a convolutional neural networks that have 53 layers, and from these 53 layers, some of them are for detection, others are for feature extraction, and others are for classification. One characteristic of the YOLO V3 algorithm that it has the possibility to detect small objects. Also, we have used the SSD algorithm, that is the single shot detection algorithm. This algorithm also uses a convolutional neural network, and it has a BGG16 algorithm. Uses a BGG16 algorithm and a lot of convolution. So in the SSD algorithm, we have an input image, and we construct a lot of map features. And in these map features, we construct bounding boxes. And these bounding boxes are compared with the ground truth of the image. For the SSD algorithm, it's usually used the BGG16 algorithm. But for our application, we have used a mobile net V2 algorithm because it was already loaded in the environment, in the software environment that we have used. We have used Google Colab in our experiments, but also because the mobile net V2, it's an algorithm that it's more computational efficient than the VGG16 algorithm. So which one was the software architecture that we have used? We have used for the YOLO V3 and the SSD mobile V2. We have used Google Colab, label image, software, OpenCV, good Darknet, TensorFlow, and TensorFlow Slim for implementation. So the methodology that we have used with YOLO and with the SSD, we have implemented, first of all, have used the software of label image to set all the labels in the images. We have divided the training set in training and test set, and we have applied both algorithms. So as a result, we have applied both algorithms in a mobile robot navigation dataset that we have implemented in our lab. This dataset contains some objects that are used for mobile robot indoor navigation. These objects are some of the most common objects used in mobile robot indoor navigation, as you can see in this slide. You can see here. If you can go up. Okay, thank you very much. So these objects that are commonly used in an indoor mobile navigation environment, we have a box, a table, a chair with wheels, and a common chair. So we applied, first of all, the YOLO V3 algorithm without that limitation, and the SSD algorithm without that limitation. So for the case of the box and the table, the SSD algorithm showed better results. And for the case of the chair with wheels and common chair, the YOLO V3 algorithm showed better results. If we apply what's the history stuff? No, it's not. It's not good. Okay. See? Sorry. Okay. So we have applied both algorithms without that update. The next slide, we can see in the next slide, the previous slide is the next slide, we can see now the next. No, the next. Okay, the previous. Okay, thank you. So in this slide, we can see the application of SSD and YOLO V3. We can see that both algorithms, YOLO V3 and SSD, they improve their performance, but the SSD algorithm still has a better performance with the box and table, and the YOLO V3 algorithm has still a better performance with the chair with wheels and the chair. We go to the next slide. So, if we use other metrics as precision report performance score, we can see that without that limitation, the YOLO V3 has a score of 75%, and the SSD mobile net has a score of 72, not 75%. So if we apply that augmentation in both algorithms and apply all these metrics, we can see that it has a slightly better performance compared with the early algorithm of 89, not 94%, compared with 80%. So as a conclusion, we can see that we have applied both object detection algorithms successfully in a mobile robot navigation dataset. Both algorithms worked, but if we don't use that augmentation, we can see that the YOLO V3 has a better performance compared with SSD. But if we use that augmentation, we can see a small improvement of SSD compared with the YOLO V3 algorithm. Also, we can see that for the same number of training steps, the YOLO V3 algorithm and the SSD algorithm, the SSD3 algorithm is faster, but in the long term, the YOLO V3 requires less training steps compared with the YOLO V3. Sorry, the YOLO V3 requires less training steps compared with the SSD algorithm. So the SSD algorithm requires 12,000 steps, and the YOLO V3 requires just 1,200 steps for training. We can observe also that data augmentation in both cases improve the performance of the algorithms. Thank you very much for your attention. I'm open to your questions.
Thank you, Daniel, for your presentation. Some questions? Some questions from Daniel?
Hello, also about the augmentation technique. What
Okay. Thank you. So we have used data augmentation techniques as rotating, scaling for the data augmentation. At the beginning, we have an unbalanced data set. So we have more or less 400 images, 200 images, sorry. We have increased with this artificial synthetic data to 1,000 images.
I have just one. Why to evaluate the YOLO V3 and not say YOLO 5, for example, or other techniques?
Yes. When Adriana was doing his her undergraduate thesis, for two reasons. First of all, when she was doing her undergraduate thesis, she started using YOLO V3. After appeared these algorithms of YOLO V4, YOLO V5. But the software that we were using, Google Colab, it was already very easy to implement the YOLO V3 in the Google Colab. And we have a lot of progress with respect with the computational power. So we have to go to Google Colab Pro, buy some Google Colab Pro utilities in order to perform the other part of the algorithm. So even with YOLO using Google Colab Pro, we spend a lot of time testing the YOLO algorithm. Now I suppose that as future work, we will use the YOLO V4 and YOLO V7. We know that have improved a lot the performance.
Thank you, Daniel. Thank you for your presentation.
Thank you. See you.
And now we'll have the next paper. The title of the paper is Semantic Superpoint, a Deep Semantic Descriptor. The paper presented by Gabriel Gam, right? Thank you.
Okay. Hello, everyone. My name is Gabriel Gama, and I am the undergrad from the University of São Paulo. And together with Nicolas Rosa and Professor Valdir, we did the work Semantic Point, Deep Semantic Descriptor. Most feature extraction methods are primarily based on photometric information, so they are highly susceptible to viewpoint and illumination change, especially in the case of handmade ones. In order to mitigate this problem, you can apply convolutional neural networks, but we are not sure if it's actively learning some kind of semantic information. So to solve this, we propose to add a semantic decoder to a feature extraction architecture. In this case, we specifically adapt the superpoint model. So just a brief introduction to the superpoint. We first need to train a base detector in a static data set created with preset key points in the joints and vertices. And this base detector is able to generalize to real-world images and create a pseudo label for the superpoint model. So originally, the superpoint model only had two decoders, one for the key point extraction and another for the descriptor generation. And we proposed to add the third one, the semantic decoder, to create an inductive bias to make the model learn semantic information and use it in the feature extraction step. So in this way, the extractor filter does depend on the final quality of the semantic prediction, being more robust to misclassification, and they also don't increase any computational costs to the first step as the decoder can be removed. So one problem of adding multiple decoders in a shared encoder architecture is that you need to balance each loss. Here we evaluate two methods, the task uncertainty weighting and the center direction. We also consider the weighting sum, but as it requires hybrid search, is very costly computationally. So we didn't implement that. So just a brief introduction to the central direction. You need to calculate a vector that minimizes the convex norm. And the authors also proposed to add a tensor component to add the type consistency. So in the specific case of the task uncertainty weighting, we adapted the article because they only proposed to the regression and classification problems that solve our detector and semantic decoder, but our descriptor decoder is trained with the hinge loss. So to solve this, we consider the hinge loss as two normal distributions, and we did a couple of considerations and approximations, and got to the final equation on the right-hand side, on the bottom right-hand side, and combine it with the other loss to get the total loss defined on the left-hand side. So, okay. So we evaluated our model in the HPS dataset according to the metrics proposed by the original superpoint article. And the semantic superpoint trained with the uncertainty was able to surpass the baseline and the superpoint trained with uncertainty as well. in the matching score method that evaluates both the detector and the descriptor at the same time, and is also the most relatable to Islam applications. Unfortunately, we weren't able to reproduce the results from the pre-trained model because they didn't make the code publicly available. We also evaluate on the case data set with considering the Obislan tool as our base framework, and the semantic reversal was able to surpass the super points in each sequence, considering the absolute trajectory error, and what was very a significant way in 3 of them, while the super point was better on at 1. And we also considered the relative pose error, where the semantic super point was better at 2 of them in a significant way, and while the super point was better on that 1. So in summary, we did a small evaluation of multitask learning methods. We proposed a new training paradigm for deep feature extractors, and we also showed that intrinsically added semantic information can improve deep feature extractor methods. That's it. Thank you for your attention.
Thank you, Gabriel, for your presentation. We have some questions. Question for Gabriel.
Hi, Gabriel. Thank you very much for your presentation. Congratulations on your work. I was
So in this case, we base our code on an open source implementation that I forget what was the name of the article, but they implemented the super points with the obvious one, and we adapted our code. But the change that we needed to do was we first substitute the order for the super points, so we have the key points and the descriptors, and the distance instead of being the binary, they call from binary that you normally has the binary distance. You use the L2 norm as your distance here. So we did this.
Questions? Gabriel, what is the main point of your work? I saw that some related works presented good results as well. How can you differentiate your work from the others?
There are other methods that implement semantic information with feature extraction, but as far as I know, they use the final prediction, so they are highly dependent on the semantic prediction of the neural network. That sometimes requires a heavier network than they use here, and to solve this, we make the model intrinsically learn semantic information. So we are not binded by the quality of the final prediction. So we are able to increase the performance while keeping the computational cost low.
Thank you, Gabriel. Congratulations for your presentation. And now we'll have the last paper, the title Linear Windows Optimization Algorithms for Fusion of Redundant Stereo Spatial Functions. So this paper will be presented by Bruno da Silva.
Hello, everyone. I'm Bruno Silva. I'm from the Federal University of Rio Grande do Norte, and I'm here to present our work with Elizabeth and Luis Marcos entitled Sliding Window Optimization Algorithm for Fusion of Redundant Stereo Visual Odometries. So here's a brief summary of our presentation. Visual odometry is the estimation of camera motion from image sequences. So we feed image sequence to our system, and then we get the estimated motion from these sequences. So this process is known to be error prone, very error prone. So error accumulates largely over time. In order to reduce this error, traditionally methods employ error minimizations within a sliding window, is within a temporal sliding window containing, let's say, the last k frames, for example. No, for Simon laser. Okay. So with this, following this traditional direction, we assume we have two pairs of stereo cameras. So we have a total of 4 cameras. And assuming this, we propose to merge two independent visual odometries into a single optimal visual odometry estimate. So as we can see here in this table, all related works that we found in the literature doesn't employ error minimization or fusion of independent visual odometries. Or which they do is to merge, is to fuse measurements from different sensors, like IMU with cameras or monocular cameras with stereo cameras, and so on. Next one. So our setup, as I said before, assumes we have a total of 4 cameras. That is 2 pairs of stereo cameras. So we assume also that these 4 cameras are able to perceive a common portion of a sensed scene. So to maximize this sensed scene, we interleave the stereo cameras. So as we can see, the stereo camera 1 is interleaved with stereo camera 2. The first stereo pair is interleaved with the second stereo pair. So from this, we have 2 problems to solve. The first one is to find feature correspondences between stereo pairs. So this is required to the second step, which is to fuse the 2 visual odometry estimates. So the first step is how do we proceed to tackle this problem is to use libviso. We rely on libviso to estimate a visual odometry for each stereo pair. As I said before, we have 2 independent visual odometries. So we keep the feature tracks, we keep the 3D estimated points, and so on. Then we discard 3D points that have depth larger than a pre-specified threshold. And for a specific time instant t, we have to determine that if some point or all of the points, if this point is visible in stereo pair number 1, if it is visible in stereo pair number 2, or if it is visible in both stereo pairs. To identify if it is the case, that is, if the point is visible in all of the 4 cameras or in just one pair of the 2, we perform feature matching between the 2 left images of each stereo pair. So by doing this, if a match is found, then we have the correspondences, the feature points between all 4 cameras. Or else we just keep that point because it will be important to aid in the process of optimizing our visual odometry anyway. So to tackle the second problem, that is the problem, the step of actual performing the fusion between the 2 stereo visual odometries, we rely on bundle adjustment, which is a reprojection error minimization that can be approached as a graph optimization problem. So in this graph, those are the parameters that we want to optimize. So the nodes in our case are cameras and 3D points, and the edges are the point projectors. As we can see here in the next slide, for example, we have these blue, the bottom part of the slide, we have the blue points, blue nodes, which are our cameras. We want to optimize these. And upper part of the slide, we have the 3 points. So as I said before, specific points can be visible in a single stereotype. So it will be an observation of type ZS, Z stereo, or it will be an observation of type ZN, Z multi-stereo. So this point is visible in all of the 4 cameras. So we construct this graph. And then we apply nonlinear optimization, least squares, with the Levenberg-Marquardt method. So the trajectory computed from the first stereodometry, the first pair, is considered as the initial guess of the optimization. So for this, we used C++. We programmed our system in C++, OpenCV, libvisor as error-based system, and G2O for graph optimization. We carried out experiments to validate and to assess, to evaluate our system with Kitty datasets, because these datasets provide, as required by our method, 2 pairs of stereo sequences. So, okay, we have a pair of black and white stereo pair and a pair of color stereo pair. In this table, we can see the results with the first set of experiments that we carried out. That is, compared our stereo fusion, third column, to the base libvisor system, first column, and to the libvisor system enhanced with bundle adjustment, second column. So, as you can see in the last column, our method is able to improve the estimate of the base libvisor system of up to 94%. And it's also able to improve the estimation of libvisor with bundle adjustments with up to 91%. This is the translation error. And the following slide shows the rotation error, which shows similar results. So our system is able to improve the estimate of up to 97% in comparison to the base libvisor system, or up to 94% in comparison to libvisor enhanced with bundle adjustments. So in the second experiment, we compared our system with OrbsLand 2 and with UCOSLand. So this is a bit unfair comparison because these systems are SLAM systems. They perform steps that visual odometries like ours don't have. So for example, they close loops. So they recognize when they pass it through a previously seen location, and then they optimize to reduce error, which our method doesn't perform. So as expected, we weren't able to have similar results to OrbsLand, but even so, with these limitations of being a visual odometry method, we were able to improve the error of up to 91% in comparison to UCOSLand in the translation error. And in comparison to regarding the rotation error, we were able to improve this error also of up to 91%. In the next slide, we can see some sample trajectories generated by all the 4 methods. So aside from the sequence 0, 1, our method was able to follow the ground truth trajectory. So in conclusion, we propose an algorithm to fuse stereodometries using nonlinear optimization as sliding window and graph optimization. We show that error accumulation of visual odometry can be minimized if using this strategy. The method has some limitations, like for example, the matching step between the 2 stereodometries is still slow. And for future works, we pretend to fuse other types, other categories of odometries like LiDAR odometry or monocular odometry. Thank you.
Thank you, Bruno, for your presentation. Congratulations for your work. We have some questions. I have one question. Bruno, why your approach does not have the loop closure step, and it's possible to implement this step?
So yes, it is possible, and it's also possible to explore the fact that we are acquiring images from 4 different sensors to even improve this loop closure method. So we have more data to more confidently, let's say, determine that we have already passed through a known location previously before. We haven't done so because this is what the doctoral thesis of Elizabeth, and her scope was to, okay, let's not tackle this problem, let's set it aside for future works. So we just have to tackle visual geometry, and that was how it was done.
Thank you, Bruno. Congratulations. We have a question.
Thank you very much. Yes, the question with respect to what is the relation of that library with the org is one group, with the org is not two, I do not know also this.
Okay, so libvisual, which is our base system, the base method in which we build our system upon, is a visual geometry method, which is part of a larger SLAM system. So OrbSLAM performs visual geometry. OCoSLAM also performs visual geometry, but they also perform other steps, which makes them SLAM methods. And while our methods, our method is only just visual geometry methods. Okay.
Thank you again. Thank you for presentation, Bruno. And now it's closed the BSM section. Thank you for your attention.
Good morning, everyone. My name is Diego. I'm from the University of São Paulo, Escola Politécnica. I will be the chair of this section that is from about control of the robotic systems. We will have 4 papers, 4 presentations. The first one will be called the Global Elastodynamics Performance Criterion of Manipulators with Flexible Joints. The authors are Fabian Andres, Lars Molina, and Didier Dumur from Central Supelec. The presenter will be Fabian, that is online. Fabio, can you hear me? Fabian? Tá ouvindo? Fabian?
Okay, I'm here.
Oh, okay. Well, can you begin?
Okay, of course.
Fabian will be the presenter. It's up to you, Fabian.
Okay, good morning, and thanks for your presentation. My name is Fabian Molina, and I'm a professor in the Federal University of Triângulo Mineiro at Uberaba, Minas Gerais. And I'm going to present the work entitled Global Elastodynamic Performance Criterion of Manipulators with Flexible Joints. Okay. Just a second. Okay, the design criteria performance are used to measure the mechanical properties of manipulators in order to quantify the performance of the manipulators to carry out a determined task. And several criteria has been used in order to perform the design of manipulators. These performance criteria are based mainly on the kinematics of the manipulators, and they are based on the Jacobian metrics. Therefore, these design criteria can be classified in local or global criteria. The local criteria quantify the properties at a specific configuration of the manipulator, and the global criteria, they quantify the mechanical properties in a region of the workspace. In this paper, in this work, we proposed a novel design criteria based on the elastodynamic performance of the manipulator with flexible joints. The methodology: first, we evaluate the elastodynamic performance of the manipulator, and then we solve the eigenvalue problem to quantify the fundamental natural frequency, or the first natural frequency of the manipulator. And then we evaluate this natural frequency in a region of the workspace. In this work, we evaluate 2 manipulators: a planar serial manipulator and a parallel planar manipulator with flexible joints, active joints. This is the outline of my presentation. First, I'm going to present the model of the manipulator and the global elastodynamic performance index. Then I'm going to present some some numerical results, and finally some conclusions. Okay, first we have the numerical model of the manipulator, and in this figure we can observe the actuator and the rigid link coupled by a flexible torsional spring. It means that this joint is flexible, and then we observe in equation 1 and 2 the dynamic equation of the manipulator. The first equation represents the dynamics of the links and the second equation represents the dynamics of the actuator. These two equations are coupled by an elastic torque as presented in these expressions. Then we simplify the model by taking into account two assumptions. First, that the manipulator is considered at a constant configuration. What I mean is that the configuration or the position of the n effector is constant. Therefore, the velocity is equal to 0. And the second assumption is that no damping is considered, which is a critical case for the elastodynamic model. Therefore, in equation 3, we have the simplified model that considers the total inertia matrix and the total elastic matrix of the manipulator. Based on this simplified equation, we can solve the eigenvalue problem in order to compute the auto values that corresponds to the natural frequencies of the manipulator. In equation 4, we can observe the eigenvalue problem. And we compute the set of the natural frequencies. We consider the first natural frequency in order to quantify the elastodynamic performance of the manipulator. Then we can observe that the mass matrix depends on the configuration of the joints. Then we evaluate the first natural frequency for W, where W is a region of the workspace. Therefore, U, which is the joint space, the joint vectors, are contained in W. And this relationship is obtained by using the forward kinematic model. And for the numerical results, we applied this methodology in two manipulators. In table 1, we have the dynamic and the geometric parameters that we consider in these numerical results. First, we have the first manipulator, which is a two-link serial manipulator with two flexible joints. And we consider the dimensionless length links, by introducing the alpha variable. This analysis is important in order to evaluate the elastodynamic performance by comparing the link lengths of the manipulator. And then we compute the first natural frequency for different values of alpha. And we obtain when alpha is equal to 1, it means that the link lengths are equal, the link 1 and the link 2, the dimensions are equal. We obtained the maximum natural frequency. And then we compute the global elastodynamic index. And we observe that when the two links are equal, we can see that the first natural frequency is is greater than the other cases. In the second case, we consider the parallel manipulator. The elastic joints are the active joints of the manipulator. First, we consider the non-dimensional link lengths. I consider these expressions, and then we define the design space of the manipulator in order to evaluate the link lengths, the properties, the elastodynamic performance as a function of the link lengths. Before that, we consider the workspace of the manipulator. In this picture, we can see the workspace. And inside the workspace, we have the singular lossy curve or lines. And we define the maximum inscribed workspace, which is a circular region of the workspace that is bound by the external limits and the singular lines as presented in this figure. And we consider this region of the workspace as W in order to evaluate the elastodynamic performance. First, we evaluate the local natural frequency, and we can see that the maximum value of the natural frequency is contained in the maximum inscribed workspace. Then we consider three cases. In these three cases, we define different link lengths as present in this definition. And here we present the maximum inscribed workspace and the corresponding natural frequencies computed for these three cases. And we can see that for the third case, we obtain the greater maximum inscribed workspace. And also we can see that for this case, the natural frequency is maximized. Therefore, we can see a great correlation between the link length and the elastodynamic performance. And finally, we compute the global elastodynamic index as a function of the three link lengths. For this case, we use the space design. And here we have the global elastodynamic index. We obtain the maximum value where the first link is smaller than the second link. And for this case, the first natural frequency is maximized over the maximum inscribed workspace. And this information is useful for design procedures of the manipulator. As a conclusion, we observe that the global elastodynamic index was applied in a parallel and a serial manipulator. And the global elastodynamic index was useful in order to evaluate the dynamic performance in order to carry out the mechanical design procedure of a manipulator. And thanks for your attention.
Thank you, Fabio. Well, we have time for one question. Questions? Fabian, only just one question. How many eigenvalues you have within this problem?
Okay, for this specific problem, I think that I have two eigenvalues, two eigenvalues, because I have two flexible joints. I think that I have two eigenvalues.
Two eigenvalues, one for each degree of freedom.
Okay, yes. Yes,
Well, Thank you very much, Fabian.
Okay, thank you.
The next presentation. Presentation will be modeling, control, and application of soft pneumatic actuators in upper limb exoskeleton. A systematic review by Leandro Goya, Alexandre Campo, and myself. Leandro, you have 10 minutes.
Morning, everyone. My name is Lars and I'll be presenting my work only control and applications of subpneumatic actuators that will access skeletons, a systematic review. Starting off with the definition of an exoskeleton it's a class of robots that extends the strength of the human body beyond its natural ability while maintaining human control of the robot, or a device that amplifies the wearer's strength and endurance. Conventional industrial exoskeletons, as the ones in the figure, are made of radiomechanical structures actuated by electromechanical devices such as motors or hydraulic or pneumatic actuators, but that makes them heavy and difficult to adapt to different body sizes, what isn't interesting for rehabilitation exoskeletons. Then comes soft robotics, that is a field that uses soft, flexible, and stretchable materials such as silicon rubber or fabric to create soft, flexible, adaptable structures that can solve the problem of adaptability to different body sizes. However, since their actuation is based on large deformations, there are no linearities that make the modeling and control more challenging. So our goal of this research was to review the soft pneumatic actuators utilized in upper limb exoskeletons and how are they modeled and controlled. We perform a systematic review in which to answer a question, we search for the main references in the literature in the field. Then we define a research protocol that can be replicated or performed, updated in the future. Then we perform the literature search in different databases and we filter the results to the ones more relevant to our study and extract and analyze the data. So our questions based on our goals were, what are the applications of soft pneumatic actuators in upper limb exoskeletons and how are they modeled and controlled? We performed the literature search and the IEEE Explore, ScienceDirect, Scopus, and PubMed databases with the keywords soft pneumatic robot and exoskeleton, and we filtered the results to journal and conference papers published between January 2016 and May 2022. In our screening process, we selected the journal and conference papers that included a upper limb exoskeleton with soft pneumatic actuators that presented modeling or computational simulation, a control method, and experiments. We selected a total of 20 articles. But there were some of them that were found in more than one database, as in our charts. The data we extracted were the description of the soft pneumatic actuator, the exoskeleton, the modeling or simulation methods, the control system, and the experiments. We classified the exoskeletons into three groups: hand and wrist, elbow, and shoulder exoskeletons. But since the hand and wrist group was bigger, we subdivided it by the type of actuators: the inflatable, bending, and suction cups. The inflatable actuators are used to stabilize the joints of the human hand and assist in certain tasks. The bending actuators are placed over the fingers, often attached to a glove. and they assist finger flexion and enhance the grasping force. The suction cups are used to assist grasping of small and delicate objects that will require more dexterity. Elbow exoskeletons use artificial muscles that emulate the muscles of the human arm to assist elbow flexion and extension. Shoulder exoskeletons use different approaches to assist the shoulder adduction, abduction, flexion, and extension, either by pulling the arm from over the shoulder or pushing from underneath the arm. Out of the 20 articles that we selected, 10 of them presented quasi-static models that describe the geometric strain and forces of the subpneumatic actuators and their interaction with the human body. 3 articles presented dynamic models of soft artificial muscles that are comprised of a contractile element in parallel with a nonlinear damper and elastic elements. 2 articles presented kinematic models of the finger and shoulder together with the exoskeleton. 2 articles presented 2 methods of system identification, one with neural networks and the other one with support vector machines to identify the parameters of a dynamic model. 4 articles presented simulation models through finite element method. 5 articles presented open loop controllers activated by buttons, switches, or a smartphone app. 6 articles presented pressure feedback controllers that regulate the pressure around the value that is established or identified experimentally. Moving on to more advanced controllers, starting with there are 2 articles with position and pressure cascade controllers. There was 1 article that presented a force pressure and position fuzzy controller. 1 article that presented a position adaptive controller for a exoskeleton. One article on a double exoskeleton proposed a force and position sliding mode controller. And another one by the same authors presented a different approach with an impedance control. In summary, there are different types of actuators, software actuators that can be applied to upper limb exoskeletons. The bending, inflatable, and suction cups for hand exoskeletons, and the contractor and extensor ones for shoulder and elbow exoskeletons. Half of the articles that we selected presented quasi-static models, but the dynamic models and finite element method models and identified models better describe the behavior of the subpneumatic actuators and exoskeletons. In the early stages of development, the open loop and pressure feedback controllers are viable options to experiment and study the exoskeletons. However, more advanced controllers like the cascade controllers, the fuzzy sliding mode impedance controllers are more robust to the non-linearities of the subpneumatic actuators and exoskeletons and to possible disturbances and noises. This systematic review is expected to help guide in the developments of subpneumatic actuators focused on the applications in soft rehabilitation exoskeletons. I would like to thank the CAPES Foundation for supporting this research. Thank you.
Thank you, Leandro. Any questions for Leandro?
Congratulations on your work regarding your research results. Asking to either do you really think that is reliant for real information? indoor restrictions.
According to the papers that we found, the most reliable ones are the pneumatic artificial muscles. They can lift several pounds and dozens of newtons of force, and they have been used for a few decades now. But there are some alternatives that are made of silicone rubber, for example, that can lift lighter weights, but can be applied to exoskeletons or some type of assistant devices. And there are the pneumatic actuators, the bending actuators that can be used as robotic gloves that don't require that much strength. They just assist the bending motion of the fingers. Questions? Okay, thank you, Leandro, for your presentation. Well, presentation will be MPC-based reference governance control for self-writing of robots. Preliminary results. The authors are Auri Gomes, Lucas Schulze, Lucas Melitol, Lars. Out. Presentation will be delivered by Auri.
Good morning, everyone. My name is Auro from Santa Catarina State University. I show here some our preliminary results of the MPC-based reference governance controller up to self-writing quadruped robots. So, the last few years, there's a lot of advantage in the research involving the leg locomotion. However, besides these new techniques become more and more robust, some unexpected situation may happen and leave the robot to a false situation. So, like lost the static or dynamic stability, situation of lost the contact points, loss of the capability to generate the ground reaction forces, and so on. So the robot must have some way to recover for its fall, and this is known as self-writing. Talk about self-writing, there are two basic ways to realize them. One, it is considered the civil way, which uses the structure of the robot to realize it, or the active way, which use the actuators of the robot to flip the robot or put in the right orientation. I show here the example for Heikyuu to Max. Realize the self-writing. In the papers, the authors create some reference to the joints and create some small filters to the robot realize the orientation. However, these situations are created to a specific environment. There is no feedback from the robot states, like the orientation or if the robot's following in a different situation, or even don't consider the constraints of the system or the environment. So our proposal is RGC control. But what is RGC control? RGC control is a closed loop control which modulate a high-level reference control, create a new reference, which can ensure some performance to the system or even consider some constraint satisfaction. We are using the MPC which is a kind of optimal control. We have considered the model, the closed loop system of the robot dynamics in the low-level controller. We can consider this as an optimal control strategy. Once we can create some optimal post function to the task, and we can consider some constraints. So in our case, we are using for the internal controller is a PD controller. The dynamics of the robot is a centroidal dynamics, which we demonstrate how the forces change the COM position and orientation. For the constraints, we are considering the ground direction forces applied by the robot and the COM position. In cost function, we are minimizing the error between the joints and the reference, the orientation error, and the control inferred. So, as I said before, the central dynamics, we can analyze how the forces contribute to the movement of the COM of the robot in the linear way and the angular way of the robot. The internal controller is a PD control applied at the torque in the torque level, but we can change it using the inverse Jacobian transpose to a force, the force space. After some mathematical procedures and work, we can find this space model, state space model, which these states are the velocity of COM, the angular velocity of COM, the joint position, the COM position, and the orientation of the robot. The control action in this case is the reference of the joint, and the last term of the equation 5 are some terms disturbed terms. We will write this model using incremental manner after do a discretization. And through the discretization, for the constraints, we are considering the ground direction first to keep the feet on the contact. We first consider to use the friction cone, but it's a nonlinear one. So we change for the pyramid form, which is a linear and proposed by Focket et al. For the COM, we are using this to ensure that the COM stays inside the convex hull formed by the contact point to avoid the robot fall during the stand-up phase and after finishing. Our cost function, as I said before, we are penalizing the error between the high-level references and the reference of the robot, the orientation error, and the control inferred, which now is the delta PR. So to compare our situation with the Semny et al. Solution, we place the robot in a flat surface and start to realize the stand-up phase of self-writing. Then, if the two options, the two proposed solutions conclude the task, we increase the angle of the grounding by 2 degrees. We did it, and as you can see, in the first plane is our solution, and the second one is the Semny et al. Our robot can stay and do a stand-up phase of self-writing, while the Semny et al. Solution fall because they don't change. It's more evident here, where the blue dot lines are our modulated result, while the black ones is a high-level solution. As we can see, our solution changes the values of the joint reference to consider the constraints and keep the robot in a stable situation. As I said before, we put some constraints in the COM position, and as the blue line shows the COM trajectory and Z and X axis, and Z and Y axis, and as bounded this with inside the convex hull formed by the contact points. As you can see, the robot stay in place. We minimize the error of the roll angle, and the constraints of the sleep in the ground, as you can see, are respected during the test. So our method proves that we can use the same high-level reference create before for a different situation. In next steps, we will extend for the other phase of self-rewriting. We are now using only for the stand-up phase. And one of the thing is topic we will address is know exactly where is the contact point, because we want to know where the robot is contacted with the environment to ensure the realizing of the self-rewriting. Reference, thank you for.
Okay, thank you, audio. Question, please.
First of all, congratulations.
Thank
you. It's not an easy topic to talk about. I'd like to ask that in many different fields, robotics, there have been an increasing presence of machine learning techniques to solve situations that were once solved by direct control methods. In your research, have you ever found references that use techniques such as reinforcement learning? Because you presented a cost function, you presented actuations, actions. So it seems, at least the first thing for me, that it would suit at least if it's working shot. So I would like to ask if you have tried or at least seen these types of techniques in your life.
Use it. So, thank you. Yes, there's some research who address this topic. I go before. Let's show. There's no slide, but there are some researchers who use some artificial AIs, but or machine learning, but there's a problem. I can extend to all situations. Maybe there's some situation which the ML can not solve the problem. In our case, we can use the ML to generate the references in our control. As we have a model, we can ensure that that references will be activated or even take more closer than respecting all the constraints. It's a basic idea where we can use a model. I will use a model, and the reference I generate in the future, is our mission. Future works is to create this reference using the machine learning research.
So they have not been proved to be reliable.
Yes, there's no guarantee of the stability of the robot. For example, imagine you are using one kind of the robot in a place, then you can go in, stand up, then with your mouth, your hands. So you want to have some way to ensure our control can do it.
Thank you very much.
Questions? Question. What should be other control strategy that you could use in place of NPC?
There are few works in 90 who use other techniques. Ben Parach proposed some strategies which we apply a reference, check if the new reference, modulated reference to the model, check if it's can be applied to the system and the system will be stable, and then apply to the system. A closed loop system. There's a few works talk about the referencing, but now with the MPC solution, it's become more evident in these last few works.
Questions? Okay, thank you all for your presentation. Next work is dynamic modeling using the principle of virtual work and the decentralized PD control of a steward Go platform. Yeah. Yes.
Okay, so good morning, everyone. My name is David Klein. I'm with the Federal University of Santa Catarina. Today I'll be presenting my paper, written alongside my advisor, Daniel Gaman, from the Federal University of Santa Maria. This paper was based on my graduation thesis. It's entitled Dynamic Modeling using the principle of virtual work and a centralized proportional derivative control of the short-term platform. So, summary, I'll be speaking brief introduction, speaking a bit about the theoretical background and methodology used, present some results. So, the SwordGov platform is a 6-degree of freedom, fully parallel manipulator. And the main advantages of using parallel manipulators over serial ones is that they have higher load capacity, they have higher structural stiffness, the load inertia is better, and while the main disadvantages is the reduced workspace and the forward kinematics problem is very difficult to solve. So that's a disadvantage of using parallel robots. Speaking a bit about dynamic formulation, when talking about robots, we mainly use 3 types of dynamic model. The first one being the Newton modeling, which has where you can compute the manipulator reaction forces, and that's good for the design process. However, because of these equations, you have a low computational efficiency, so that's a disadvantage. Here's the Lagrange method, which has a better computational efficiency than the Newton-Euler method. However, you cannot find a closed form solution for the dynamic equations, so that's a disadvantage of it. Then you have the virtual work principle, where you have low computational cost because of the D'Alembert's principle. That's because you do not compute the manipulator reaction forces. That makes this methodology to be better suited for simulation work. That's why this was chosen for this paper. Speaking about a little bit about control, we have a middle system, which have both the input, both the output, and we can use various control techniques to control middle systems, advanced control techniques. But in order to simplify the problem, we use the simplest way to control the manipulator, which is usually decentralized controllers. So that means that each one of the actuators have one single control. So the generalized SwordGov platform, it has obviously a fixed platform attached to a moving platform. It is attached by 6 SPS kinematic chains. The kinematic chains can be run in order to create different mechanisms and different robots. So we have a spherical joint followed by prismatic and another spherical. So the inverse kinematics of this manipulator is presented by this big equation, but it's pretty straightforward problem to solve, given that you have this vector sum. So it's pretty straightforward and intuitive. And this is the equation that models the closed open loop form of the dynamic equation using the principle of virtual work. But that open loop equation is not suitable for control purposes. So that's why it was needed to find a closed form solution in order to perform control techniques and to reproduce techniques that are used in serial manipulators as well. So this is the closed form solution. We have here a mass matrix and a OEE and a centrifugal forces matrix. The gravity vector taken into consideration as constraint force. So this paper a controller. Controller used was the simplest one, which is a proportional derivative controller, and it was used in the manipulator's test space. This was chosen because mainly to avoid the problem of the forward kinematics. So, and to use this test space technique to control the manipulator. So here we have a diagram, the simple control loop, which we give a reference with the generalized coordinates or the n factor of the manipulator, which are the position and orientation. It calculates an error, has to be to the PD controller, and we get this force distribution one, which transforms using the Jacobian matrix the manipulator forces towards into the actuator forces, and then we pass through the system dynamics. So all those simulations were made using MATLAB. They're all implemented in MATLAB. Using the functional E45 mainly to get this numerical integration of the dynamic equation, and in order to calculate the control action of the system. And then all the physical parameters and the trajectory were taken by the paper of design, which we presents the modeling, the open modeling is the principle or to reproduce the experiment results. So this is a reference trajectory applied. We don't have any rotation applied to robot center factor, and we have this sinusoidal translation applied to each of the robot's axis. And speaking a little bit about results, this is the inverse kinematics calculated using the equation. See that there are pairs. The inverse kinematics gives the actuator lengths compared to a dimensionless time, omega t. So those are the actuator lengths that are needed, required for the robot to complete the trajectory desired. The inverse dynamics was also simulated and is presented here as the output or the actuator forces, which are necessary for the robot to perform the trajectory tendon. So we have the actuator forces versus a dimensionless time as well. The results of the proportional derivative control for x-axis motion, and the left graph we have the x-axis translation. So it's a little bit hard to see, but the orange one is the desired trajectory, it's the reference trajectory, while the blue line is the executed trajectory line. And the right graph, we have the x-axis rotation. The same thing, the orange one is the reference rotation, which is 0. The blue one is the executed trajectory. You see that the manipulator had a few initial position, an initial position in order to execute the trajectory. We have the y-axis motion as well. So we have also in orange the reference trajectory, in blue the executed trajectory, or the translation in the y-axis. And the right graph, we have the y-axis rotation. It's the same thing. And finally, we had z-axis motion. Left, right, we have the z-axis translation, and the right one, the z-axis rotation as well. So finally, we have the translational tracking error. Here, it's a little bit hard to see as well, but we have the error for translation in the x-axis, in the y-axis, and the z-axis. Finally, the rotational tracking error, which we have here the same thing as the translational tracking error, which is the blue line is the x-axis error, the orange one is the y-axis, and the yellow one is the z-axis. So, thank you very much for your attention. Anyone has questions?
Any questions for David?
I have a question. Do you consider to use the quaternions for the model?
That's a good question. As this paper was based on my undergraduate thesis, I haven't learned yet quaternions and spool theory, for example. But nowadays, it's much more feasible to use advanced techniques such as spool theory and quaternions. So at Lucy, we work a lot with that, with Davis's method, spool theory. It's a little bit hard to learn. The concepts are a bit abstract, but the results are better. So definitely, that's a great question.
More questions? Okay. Thank you, David.
Thank you.
Presentation. And it closes the section. Thank you very much for the presence. And let's go to the coffee break.
Só ficar na frente da câmera.
Vai participar.
Não, é só falar com ele.
Ou não precisa?
Bom dia. Tudo bem, Pedro? Você me escuta? Eu tenho que chegar mais perto aqui.
Liga a câmera.
Olha, Pedro.
Não percebi se estão a falar comigo.
Olha, agora sim, Pedro, eu te escuto. Tudo bem, Pedro? Prazer, o Bruno. Tudo bom?
Prazer também, tudo bom.
Que legal ter você aqui conosco, Pedro.
Bom, na verdade não estou aí convosco, era mais legal.
Seria legal sim ter você
Está,
aqui.
está ótimo, está ótimo.
Mas olha só, Pedro, quem vai ser o mediador da sessão é o professor Júlio, ele está aqui, tá? Chega mais perto. Pedro.
Viva!
Beleza, o pessoal tá voltando do coffee break. E aí, assim.
Era isso que eu ia perguntar, pois. Não estava a perceber.
Isso, não dá para ver, mas o pessoal tá voltando do coffee break. Assim que eles voltarem, a gente. Já está na hora. Eu vou chamar.
Pedro, você consegue me ouvir sem o microfone?
Agora estou a ouvir perfeitamente, sim.
Ótimo. Então eu vou fazer o seguinte, eu vou deixar o microfone para as perguntas.
E vocês ouvem-me e veem-me bem também?
Tá ok. A gente consegue te ouvir e consegue te ver. Tá tranquilo.
Já agora, se calhar, vou também partilhar o ecrã. Ainda por cima, eu estou mais habituado a. Eis, olha, ainda bem que fiz isto. Já está aqui o Mac a pedir para eu dar ao.
Pode tentar aí para dar uma testada.
Pois.
Testa os seus vídeos.
Eu tenho um Mac há pouco tempo, um Mac novo, e ele não tem alguma destas autorizações. É esse o problema. Olha, aliás, vou ter que sair e voltar a entrar, está bem?
Tranquilo.
Ok, acho que é rápido.
Ele disse que entra já por causa do Mac. Precisa fazer uma liberação.
Cá estou outra vez. Agora está-se a queixar de uma coisa diferente, mas agora já não é um problema daqui. Vocês têm que me declarar apresentador, senão ele não me deixa partilhar.
Sim.
Já está.
Ok, já consigo. Onde é que ele está? Onde é que ele está?
Tentar testar alguns vídeos que você venha a ter, porque é importante que fique legal. Se tem algum vídeo só.
E se é a questão da partilha, também às vezes há problema.
Para quem você quer enviar?
Agora está o Siri está a querer falar, não sei o que é que eu disse, mas isto não costuma acontecer. Vejam, para já devem estar a ver o ecrã, mas sem estar cheio, certo?
Sim, senta cheio.
E se eu agora fizer full screen, está bem? Ou vêm as notas?
Ok, já olha.
Tá? Ok. Ótimo.
Você tem algum vídeo na apresentação?
Vários, tenho muitos.
Testa algum deles, sim.
Então, se calhar testa-se já aqui no instante, sim. Por exemplo, estão a ver bem este? Aqui?
Não conseguimos. Não ouvimos nada. Tem algum som nele? Ou não?
Não tem. Por acaso no Zoom eu tenho maneira de dizer que quero que o som seja partilhado, mas aqui não sei como é que se faz. Acho que não há nenhum que precise de som, por isso não é grave.
Ótimo, ok.
E se precisar, eu não estou a usar auscultadores e portanto ele deve dar através do próprio Mac também. Mas este não tem. Mas está a saber bem?
Tá ok. Dá para ver. So let's switch to English. I will start the session now. I'm Professor Julio Mello. I will be chairing this session for Professor Pedro. So good day to everyone. It's nice to meet you here in Lars. Professor Pedro is a full professor at Instituto Técnico of Lisbon, and he has a PhD in electrical engineering that he obtained in New York, USA. And his major research interests are on formal approaches to several areas in multi-robot systems. He has a personal passion about in dedication of his life on robot competitions, and he's going to present his lecture on UGVs for multipurpose operations from robot competitions to real-world applications. Thanks, Professor. If you want to start right now, it's okay. I think we have 1 hour to your presentation, so the screen and the audience is yours.
I guess you are watching the PowerPoint and maybe me on a small window. I'm not sure. So hi to everyone. It's a great pleasure and an honor to be invited as a keynote speaker for this conference, which I've heard about several times before. And also it's really particularly interesting because of being in Brazil. So bom dia to brasileiras. Today I will actually, so can you see the full screen now, just to make sure? Can just someone, yeah.
Yes, we can. That's okay.
Okay, perfect. So yeah, thanks for the introduction. In the introduction, you said that my interests were in formal models and also in a big passion about competitions, more formal models of multi competitions. Today, I chose also because of the nature of the conference to be less, let's say, on the formal side, to be more on showing things at work and how did we approach them, and showing things that were motivated initially by competitions, but then we applied to more, say, real world aspects. So my talk will have no formal aspects, let's say, so point people that would be more expecting that, but on the other hand, will be full of kind of more practical oriented slides and lots of videos showing things that we did. The work is of course the result of the work of a lot of people. I have listed here in the first slide the people that collaborated particularly in the project that I'm going to talk about longer. Then in the end, I make a short reference to people of other projects, which I will show in the last slide, which also have to do with competitions and things that transited to the real world. So the main focus, as I was saying, was to UGVs for multi-purpose operations, and then from robot competitions to real world applications. And this is an outline of the presentation. I will just do a very brief institutional introduction so that you know where I'm from and what we do. Then motivating the work, and then the novel manipulators. Then on the application that we did after the first part, which is more about the competition, the application we did recently in a European project to a more real world scenario. And then in the conclusions, I will refer to other types of things that we did in competition. So it will be a relatively long conclusion with at least compared to what is usual, and future work, just listing some ideas. Okay, so let's focus first on the institute side. I could have a lot of them, as you can imagine, but So I am from the Instituto Superior Técnico. This is the largest engineering faculty in the country, and it's a faculty of the University of Lisbon. It used to be with the Technical University, but the Technical University was fused with the Lisbon University, and now there's only the Lisbon University. And inside IST, there are several research units. One of them is the so I think you see my cursor, and the symbol of ISR is here. The symbol of IST, the Technical Lisboa, is here. And my group within ISR is one of the 5 groups within ISR. I coordinate this group, Intelligent Robots and Systems Group. Here's the logo. And we have, actually, we are a quite eclectic and heterogeneous group, because we focus mostly on approaching complex systems from a holistic standpoint. What this means is, instead of focusing on navigation or control or vision, perception in general, we really are more interested on putting these things together in robot systems. Of course, there's always some focus anyway, and one of them, which is probably the one that is more similar to this usual approach of concentrating in one subsystem, is to planning. We do a lot of planning, particularly under uncertainty, and we always try to drive our research from application, be in the lab, but I mean the problems of the application drive even our formal approaches. We have a lot of things with indoors robots, but lately we also went outdoors with the UGVs, unmanned ground vehicles, and UAVs, unmanned aerial vehicles. A lot of this was driven by robot competitions of different kinds, particularly RoboCup. I am a trustee of RoboCup. I was for a while, then I stopped, then I am again currently a trustee of RoboCup Federation, and it has been there, participated several times with soccer robots, now with at-home robots. There were people here that also participated in search and rescue. So it's a long-term connection. I also coordinated one of the 2 first projects on organizing robot research-oriented robot competitions in Europe. It was called the Rockin, and we also started, and it's still running, the European Robotics League. And there were several motivated by this, where we also had competitions. One of them just finished, called She-Rock, here. And we also had, and this is a big part of my presentation, a participation in a big competition that has taken place twice already in the United Arab Emirates, in Abu Dhabi, called MBZIRG. Okay, so let's go for the motivation of the title of this presentation. So multi-purpose. We know that one of the major problems in robotics, even these days when things are becoming more and more sophisticated and even commercially successful, which is great for robotics, is that the systems tend to be limited to very specific applications, even when they are great. I mean, we see, for instance, Boston Robotics robots doing amazing things in terms of locomotion, of the whole dynamics of the system. But of course, I mean, and this is not they are essentially limited to moving from one place to another, maybe to do some inspection, maybe to carry some boxes, but of course they are not general purpose robots. And so every effort in the direction of multi-purpose robots is good because it extends the range of possible tasks. And when we do that, we have to also take into account, and there's people more and more focusing their research on this aspect, on the modularity of both the software and particularly having as a goal that you can transfer across robot platforms, across application domains, whatever you develop. Like if you have a navigation algorithm, you can quickly be able to use it in another robot, not just in the one you developed it for, or in another application, indoors, outdoors, just modifying the sensors and some parameters. Also part of competitions, and I think maybe I don't have to do a big effort to convince you, because many of the people there are motivated by this, but it's because the way I see, the way we approach them here, is that not just for education, for which they are definitely very interesting, but really to push the state of the art on research and development. It's even like having another paradigm. Instead of just going to conferences and presenting papers, okay, and a traditional but impactful way of doing things, you can also have a common problem and see what are the approaches and the success of the different approaches that people come up with to solve that problem. And the more challenging the setting is, the more the research is pushed. And we have also been pushed to do benchmarking, such that we can do something very unusual in robotics, compare the different approaches in several aspects, how good they are, and not just to say, well, look, mano hands, my robot works. Okay. And one of these competitions, as I said, that we participated was just before the pandemic situation started, was MZIRC 2020. And we participated together with a team from the University of Seville and another one from CATEC. It's like a tech transfer center in Seville. They are more focused on UGVs. And in fact, we went for it because of a project that we were going to get into later on, which is the project I will tell you about later in the presentation. And we wanted to start having this motivation to build our robots, to make them very versatile, flexible, so that then we could use them for the application. And we really had to develop, in our case, a multi-purpose manipulator, because the two challenges where we participated were very different. Challenge 2, this one here, had the goal of having a team of robots, UGVs and UAVs. Again, I will focus on the UGV only here, to autonomously construct a structure using a set of brick-shaped objects. That's what you see here. They have different colors, different shapes. My mouse is very excited about this. So brick-shaped objects. We had a pattern that we added to follow in order to build this wall. And of course, this has applications in manufacturing and civil construction scenarios, so that you give kind of instructions to the robot about a pattern of structure it has to build. And the UGV task was to build a wall by picking the bricks from places where they were, several of the same type in each block, in each cluster, and then take them to the wall and putting them in the right position, so respecting the pattern. Of course, in order to do this, we had to put together several functionalities, in particular navigation, object perception, object manipulation. And our strategy was to, and these things are the ones I'm going to focus in more detail in my presentation, so that it can sort of inspire people to at least understand how a real system can be done and work all integrated, was to first decompose the wall pattern in a sequence of bricks, then going to pick up the bricks in an order, so navigating collision-free to the arena, align with find where the bricks were and localizing them, then approaching them along with the pack of bricks, and then being able to pick them and then do again a motion to the wall, aligning again and being able to place the bricks. This was challenge 2. Challenge 3 was about a team of UAVs and UGV collaborating to autonomously extinguish a series of simulated fires in an urban high-rise building firefighting scenario. We will see pictures of the actual scenario later, but you can see here kind of the idea, a tower that can have fires inside and outside, and we should go there with water, put off the fires, also with blankets. In this case, they were taken by the UAVs. And the idea was to have them all in parallel, putting off these fires. These were simulated fires. We will see how we could test whether the fire was put out or not. And of course, this is important for applications of urban firefighting, outdoor and indoor environments. In the particular case of the UGV had to go inside the building, detect the fire. There might be two possible fires, and one of them would be active, the other would not, but we did not know a priori which one. So we had to find it and then put out that fire by throwing water at it. Here, there were more functionalities required. So besides navigation, fire detection, aligning with the fire, so all using vision, and doing calculation, shooting the water. So you need to actuate a hose that takes water from a reservoir and sends it. Planning all this sequence of things to be done. And also, particularly in the navigation, this localization switch has to do with the fact that we had to navigate outdoors and then indoors. So we had to switch the set of systems we were using to do the navigation, depending of whether we were indoor or what you see here in the picture is the simulated fire. We first did this in our lab just to test things. Then it's similar to what is done inside the building in Abu Dhabi, but of course in a much more realistic scenario. So let's see how we did it. So that's the next point. I'll talk about the hardware description, the software architecture. I'll focus a lot on the navigation and localization, about the task coordination, and then I'll show the things in the actual scenarios of the challenges. So to do this, we have developed a mobile manipulator platform, which I have shown before, but now I'm going to detail a bit more. This is based on an old chassis of iRobot ATRV Junior that some of you may remember or recognize or even still use. But we modify except for the motor. So inside, all the electronics, computers, and so on are completely different. And this was done with strong support of a spin-off of ISR called IDmind, a Portuguese company in robotics. And on the top of that, literally on the top, we had to also adapt, this one was recently acquired, a manipulator, UR5E from Universal Robotics, which, as you know, as usual in manipulators, had a control station that was supposed to be standalone. The manipulator would be fixed to a location. Here we had to adapt all this, power it by batteries instead of the AC power, and put it on the manipulator on the top of the robot and all the electronics inside the robot. This was then successful. The robot has been working quite flawlessly so far. And so we had a new mobile manipulator. I'm not going to go into details here of the hardware and how packed it is. So you have kind of two stages inside. On the bottom stage, you see the old motors, and then you see the batteries and all the boards for controlling the motors and power amplifiers. While on the top one, you see there's the NUC here, which is the processor, and then all the boards required to both control the manipulator and the UAV. If we want just to kind of take a higher level view of important things which are present, I'll focus on actuators and sensors. And what we have is, so besides, of course, the chassis and the manipulator, we had an Ocuyo laser scanner here in the front, an IMU, inertial measurement unit for navigation, GPS for the outdoor navigation part, and RealSense depth camera. We opted by a RealSense because we wanted to do things later on outdoors while use another RGBD camera, but it would not work outdoors. And in this case, this is for the first, for challenge 2, we have a magnetic gripper, but that's one of the modules we change from challenge to challenge, and we will see that then we have something more related to the firefighting. Well, you can see here a depiction of this in a cartoon if you want. So it's the same thing. But now here I have the functional diagram. And so essentially what we did was this. We have a perception module which puts together information from the 2D LiDAR and from the RGBD image. And this perception module generates two things. It generates events for the planner, for instance, when it detects that the robot has crossed the door and so it has moved from outdoors to indoors. And at the same time, it detects obstacles, determines their location, and that information to the navigation module. It detects obstacles for obstacle avoidance, and the navigation uses that together with the traditional things, odometry from the robot, and also GPS plus IMU. Okay, which of course are used for the outdoor part, while here odometry plus the environment scan done by the laser are used for the indoor part. The navigation, of course, sends the desired velocities to and it should be noticed that the planner actually determines goals to two subsystems. One of them is the navigation, of course, so it's the planner that tells what is the next goal of the navigation, say going to one of the possible fire locations, but it also tells the arm configuration, so that the manipulation module can then make the arm move accordingly, like to pick up the brick. So we put together a state machine, which in ROS was implemented using the state machine library SMAC, where we implement the plan. Basically consists of going to the pile of bricks, then aligning with the pile, then picking a brick, go to the wall, align with the wall, and placing the brick, and continue doing this. Well, assuming that here it gets formally a list of bricks to be picked that it should pick in a given order, so that it builds the desired pattern in the end. For localization, as I said, we use this relatively traditional approach of putting together IMU data, wheel odometry, and GPS. Essentially, we did two blocks here. We transformed the GPS to the same, so from the latitude, longitude, and altitude frames to the frame that we were using for IMU and for wheel odometry. And we used an extended Kalman filter to fuse all this information and estimate the robot pose. We went to, this is in the campus of IST, and it's accelerated. But we went there because we have these patterns on the ground, which we can use to visually inspect if the robot is following the path that we wanted, which, as you can realize, is on the top of these black parts of the ground. What you see are two views of the robot doing that, one close view, one more far away. And the robot is here in this case, for instance. And then here, what you see are the robot together with the ellipses of uncertainty in the place where the robot is at a given moment. When we use different components of navigation. So making a long story short, what we can observe is that the trajectory becomes more accurate as we add to originally odometry, which is this very bad trajectory here that quickly drifts. When we add our IMU in the green method, and then GPS, and also corrections with RTK, real-time kinematics GPS. And so as expected, the navigation gets better. The ellipses of uncertainty also get smaller as we add this. But of course, we needed to have waypoint navigation. We need to avoid obstacles. And for that, we built a simulator in Gazebo. We used all the artillery of ROS by using our EKF, but adding the the obstacle navigation. So you can see here, for instance, there's an expected brick on the ground that the robot avoids. And we have used the dynamic window approach local planner to follow the path from waypoint to waypoint after planning a global path using Dijkstra algorithm. So essentially, we have the localization is made in an occupancy approach, and we have cost maps that represent the obstacles and kind of the strengths around the obstacles, forcing us to avoid them. The relative localization and navigation system has to do with the part of aligning with the bricks. I mean, in this sequence of slides, you will see often a few pictures of the simulation, in this case here, where you see Cs, and down here, the real robot still in our campus doing the actual local navigation. So what the robot is doing is to use the laser scanner in front of the robot to detect a line, to estimate a line that corresponds to the front, the border of the brick, so that it can align with that line and then be facing the brick centered with it and in a position which is aligned, calibrating then both the motion of the manipulator and the view of the camera for finding where the brick picking point is and to pick it the best possible way. So this is a closed loop navigation controller that aligns with the brick. The grasping itself, the picking, is done using vision. So we have the real sense here. We have first to do this motion such the real sense can see without having the. It takes a bit of time in order to determine where this thing, which is a metallic plate on the top of the brick, is, and to determine its center. As you can see here, the object is segmented by color and by shape. And then using the magnetic gripper, because this is a metallic plate, it actually picks the brick. We use the force feedback of the UR5E to indicate that we have picked the brick. That is, we are doing enough force for the magnet actuator to work. So that's why we do that part very slowly, because we don't want to do any damage to the brick or to the manipulator, and we want to check carefully the sensor. As for a brick placement, the strategy is relatively similar. We need just to be careful that we need to know where to place the brick, and that sometimes is with respect. In this case, it's on the top of brick blue and to the right from the viewpoint of the robot, to our left of brick red. And so again, the real sense has to observe the scene to see if it is as expected, and then position the brick, in this case with a small error, with respect to what it was required. We did, of course, it's actually a good practice, and it was important for us, a lot of simulate at least the logical part of our system. So you can see a lot of the things I told you here being performed beforehand in simulation, and it was a quite realistic simulator, and it's very important to do that if you want to make sure that when you go to your real robot, where things of course are not the same as in the simulation, at least from the viewpoint of the state machine, from the logical set of operations, everything works fine. And then at least you are ensured that if you have problems, its perception and or the actuation are not working as well as you would like them to. This is already in Abu Dhabi. We did first some indoor tests with the same thing we had here, now with a larger brick, which is more challenging. And at the same time, on the right, you can see us already in the actual arena. You see the robot. Well, I'll show you then a video with a little bit more lengthier segment showing the robot approaching, avoiding obstacles, and then going to the pile of bricks. In this challenge, we could not do everything well because we would have troubles, as I will show you here, which we did not have indoors, with picking the brick because of the incidence of the sun. that would create a problem in the image, leading us to pick the brick slightly to the side of the metallic part, which means that then there was an induced torque that would let it fall. Sometimes it could pick it better for a longer time, but with this is that we would be able to fix it, but we did not have many runs. We could not even go to the arena before the first trial, which made things very challenging. For challenge 3, here are things we had to do, and then I'll show you both challenges in a longer video. The most important thing was to be able to do navigation outdoors and indoors, and to make sure that that navigation would be actually well switched when the state machine would decide that we had to move from outdoors to indoors. That is when we see the door and move there. And so we developed both ways of navigating. Outdoors using move base with the ROS move base with, again, the dynamic window approach, using a map, but also, so we had a map of the outside also, and particularly odometry plus IMU plus GPS. Indoors, we could not use GPS, so we would do essentially a map-based scan matching approach plus odometry. And we actually did not use, like outdoors, the extended Kalman filter. Here we have used Monte Carlo localization, including the adaptation to avoid kidnapping robot situations. You see here the map that we have obtained, which includes the outdoor and indoors part. We will see then the real scenario. And the switch here. So just to, in a more ROS-like jargon, you can see AMCL uses the scanner. The EKF is implemented through robot localization, another package that uses odometry, IMU, and GPS. And we need to determine when to switch. The fire detection, so we are in challenge 3, was we trained a neural network using tiny YOLO with an RGB image with real fires and with our simulated fire, and then the real fires help because the simulated fire is quite realistic, as you can see here, it could pretty well determine where the fire was once it was in the region where it would look around and find and look for one. And we also used a small thermal camera that would tell us where in the fire the hottest parts were, because we wanted to throw water at those parts, since of emulating putting off the fire would be to fill a reservoir of water. And for that, we had to really target a circle with a relatively small dimension, which was located at the hotter zone of the fire. So we also needed this in order to then calibrate, control our manipulator to throw the water to the right direction. This is the real things, one of the possible places for fire. You see here the circular window that I told you. The other one actually is there. So the robot had to come here, and because of all the calibrations we had done for the water powering system, we wanted it to be at a given distance of the fire. And of course, we wanted also to see the fire and to see the hottest, to then calibrate the height of the manipulator. Because in this case, excuse me, we removed the magnetic gripper and we put here hoses together with 2 water reservoirs, and this way we could throw real water to the system, and we have this coverture on the top of the robot, because otherwise water and create troubles to the electronics. Again, we could do the same we did with the bricks, aligning the robot with the wall using the laser, and we could just compute the target distance that we wanted. You can see, and of course then checking, as I said, with a simple controller, the height of the manipulator that would make us point at the hottest part of the fire. We actually did all this, and the trick was to use a shooting pose calculation, which is the robot comes from anywhere and reaches a waypoint which is on the top of a circle with a given radius with respect centered with the fire and with respect to the fire. And the idea is that the robot, when it reaches that waypoint, it corrects itself until it actually really is at that given distance equal to the fire. And then we have here the water pouring system actuating. You can see us testing it manually. You can see it working here with a hot plate, and here as well. You can see it's throwing water from time to time. And here you can see it actually, one of the hoses working well, another one not so well, so that you can see the relevance, the importance of throwing water at the right spot, and the more the better, so that we accumulate a lot of water, and that means we put out the fire better. So that's the direct way of doing it instead of really putting out a real fire. We had a quite realistic simulation environment so that we could still in Lisbon do all our tests as well as possible, including the entrance in the building and then doing the map of the building and navigating there. Of course, in the real place, we had to do this all with a real robot. The task coordination was again a state machine where we go to outdoors to the waypoint door, then we switch localization to indoors, and then inside the build, so we enter the building, and inside the building, we go to the waypoint that we call the check fire one, that's in front of the first possible fire position. We detect the fire. If we detect it, we align with it. Otherwise, we keep insisting and trying. And sorry, we go to waypoint check fire 2, so we go to the other because this one was not active, and then we detect the fire, and if we detect it, we align with the fire. If the two fires were not detected, something wrong happened, and the robot, instead of stopping and giving out, goes again to the first checkpoint in order to determine if it has overviewed the fire there. After aligning with the fire, you just do shooting water and then getting out, switching localization to outdoors and returning to the starting point outdoors. We actually also simulated it, so you can see the robot navigating. You can see here the point cloud, the robot, in this case, navigating outdoors. Here you have the state machine and the different states, so it's going to entrance. When it crosses here, you can see also the cost maps. When it enters here, it goes to inside the door, then it will go to one, so it will go to the right, and that's room 1, so it will move to room 1, and so on and so forth. Let me show you also, for the sake of time, the real thing, so that you can see what the robot effectively does. On the left, you see the map we built, and in a given situation, the robot laser scanning, showing that he is very well localized, such that the scans are on the top of the obstacles. You can see a video of the robot moving, and effectively you see the robot already inside the room here. It has to enter the room by avoiding the obstacles at the entrance. The fire is there. The robot knows that there's a set point here. It should align itself looking at the region where the fire is expected to be. It might not be there and might be in a second point, but here there was only one. So it may have some errors while aligning, then it compensates for that by moving back and to achieve the desired distance, because the manipulator and the hoses are calibrated for this desired distance. Sorry for the rotation, but well, then it puts the fire. In this case, it does not throw water, not to flood our lab, and then it moves out. This is the actual scenario of the competition in Abu Dhabi. Quite amazing. I mean, these people put a lot of money on these competitions, both to the teams, to the prizes, and to the construction itself. We can see actually all the scenarios, though it's not clear the one for the wall for those who were not there. But I mean, this thing here corresponds to a third challenge that we did not get into, where a quadcopter around and chase a ball that was being pulled by another quadcopter. The wall, the bricks and the wall was in this area. And this is the building where the fires are. The quadcopters could put out some fires outside here. And the inside was this region here. And you see our robot moving outdoors and then finding the door and start indoors. And then indoors, well, in fact, outdoors and indoors, you could see here simulated fire outdoors that had to be put out with a blanket picked by the UAV. And indoors, you had already had a glimpse of it. Now you see the full thing. So the robot needed to know where it was, to go in front of these two places where there might be fires. And then after firing a fire, shooting water at it. I have a video that we did for our performance in these two competitions. I will let it run, making only sporadic comments. It has sound. It's not relevant, the sound, but you will tell me if you can hear it or not. Can you hear the sound? Gustavo, can you hear the sound?
Yes, we can. Yes.
Sorry?
Yes, we
yes
can.
Or no? So here you have the different steps of the localization that I mentioned, still in our campus, the laser-based alignment, picking the brick, detecting, again, using vision, the brick place for place, and also a situation more demanding where the brick is quite close to the wall, and so it's more difficult. But particularly that then you have to look at the pattern, and you could put it in several different places, including on the top of the red brick. But here we wanted to really put it on the side of the red brick. And then this you have seen already, so I'm gonna kind of jump over it. In a real performance in one of the trials, you see the quadcopter also ready to fly, to put its own bricks. And we go to the pile of bricks. We avoid that brick which is on the ground. And then we go, as we have seen, everything is done autonomously, well understood. We go there, we try to pick up the brick, and we have troubles. You can see that the second try does a little bit better, but also not completely well. And the explanation written here is the one. You can see now that it's not really centered, and that was part of the problem. It's for challenge 3, where we did quite well. This is first in our lab. So we come from outdoors, and we switch to the navigation indoors when we cross that door. Now we are using Monte Carlo localization. And this is the part that we also saw. So we can also do yes. And now you can see, have a better picture of the actual scenario in Abu Dhabi. You can see us doing the map inside the building. And then the outside parts, just for you to have an idea. Now, you see in the competition trial, the robot first moving outdoors using GPS and common field IMU, then determining that it's at the front of the door, rotating towards the door, now moving inside, And when it crosses the door, the state machine switches the localization system to not using GPS, but laser scanning and map matching together with Monte Carlo localization. Of course, we could not be there inside to video record, but we had that of the organization, and we recorded them. You can see here the robot first looking at the first waypoint where there's no fire, and so it will try and there's no fire. We just cut it to make it quicker, and now he moves to the other one, and there is a fire, simulated fire, well understood. And so the robot detects it, and now you can see down here the tank meters, the water meters, and we won this challenge actually. So money and glory, we were very happy with it. Okay, so as I said, what we really wanted at some point, well, besides winning the challenge, was to move to an European project that was about inspecting photovoltaic plants using teams of UGVs and UAVs. Well, in fact, it was also for wind farms participating in that part of the project. And so essentially, we had several functionalities that we had to develop to address a scenario that I will show you in the next slide, which was kind of the motivating scenario, for which we did a lot of contributions. Well, just quickly to say that the project was called Durable, was an European project in the program Interreg Atlantic. It had several partners in the Atlantic area, say in academia, Bristol, the University of Seville and CATEC, ourselves and STI in France, and then several companies. These are, for instance, the Portuguese power company EDP, but also companies that work on determining patterns in images, in this case, to detect the effects of the panels, companies that are interested in having autonomous vehicles, solar and wind farms. There were several different companies. There was also an academic partner from Ireland. You have the link of the project here. I can then send you the slides. So the concept is depicted here. We have UAVs of one type. They just fly to oversee the solar panels and be able to check if there are defects. And because they have limited energy autonomy, there are two types of ones where the UAVs can land to recharge, and those that, like ours with the mobile manipulator, that can also go to some points. The panels, at least in some installations, are very low and close to the ground. And so with the manipulator, they can reach part of the panel. They can even be called by the UAV to do a closer and more detailed inspection of the panel. In the missions we did in a real scenario in Portugal, that you can see up, this was a real photovoltaic park. The navigation is also difficult because of the bumpy and grassy terrain. When you go inside the corridors between panels, GPS tends to get troubles because of all the metallic parts which are there. We have used two autonomous ground robots, a ClearPath JCal that we bought more recently, and the ATRV Junior mobile manipulator I told you about. The JCal had a Velodyne for 3D reconstruction, so it's a laser image, and it could navigate using waypoints, even using the information from the reconstruction of the farm obtained by the Velodyne, while the UGV, the ATRV UGV, used GPS plus IMU. We could also do GPS in the JCal, but it was not the main point. Using GPS was mostly in the ATRV with an IMU and odometry. And also we added the arm with thermal cameras to do the inspection. Use the Okuyo laser scan to do scan matching and be able to do map-based localization using the 3D reconstruction obtained by the LiDAR in the JCal. We also used, I mean, in this case, we had a bit of responsibility for the UAVs that were mostly with civilian CATEC. So we also used an UAV of our own that we landed safely using vision on a UGV, showing the concept of landing on a UGV to reach charge. We also worked with our French partners and with Seville on some other tasks that I will show you in a summary video. The autonomous navigation was again similar to what we did in MZIRC, but now we needed several waypoints to go and go through the corridors in between panels from one place to another. So we did one point-to-point navigation of both the UGVs. The UAVs also did point-to-point navigation on the top of the panels. We also have doing that, and then they had to land on the UGVs. We added to the extended Kalman filter with the odometry, GPS, and IMU the possibility of having matching of the data acquired by the Velodyne. That is a map. And in fact, we did several things. We even now submitted a paper with this. So we tried to match the information of the map obtained by this Velodyne 2D laser to the image with both the Velodyne itself, with so the Velodyne, which is 2D, the Ocuyo laser scanner, which is just a scan plane, and also with the information of depth from an RGBD camera. And we could reduce the mean square error from the 0.3 meters that we had with GPS using RTK to less than that, thanks to this added matching. We did something else that I will show you, but for now, this was the thing I wanted to show you. We have geolocalized all the information, so you can see this superimposed on a Google map. You can see the cloud of points that represents the map. You can see the map obtained by the Velodyne. You also can do we did another thing which is interesting to reduce the complexity of the matching, which is to segment the points. So we have here in green the points which are on the ground, in yellow the panels, and in red the metallic parts that support the panels. And then we could just do this, the matching, not with a full point cloud, but with the sub-point clouds corresponding to each of these groups. And in fact, eliminating the ground. We could take images with the thermal cameras. In fact, we could take from the frontal side and from the back side, because some techniques may allow us to do better defect inspection by having a robot from the view with an arm and an UAV from the front and doing the inspection simultaneously. We have some work in that direction, which I will not show here. But I will show you the video, which summarizes all this, a very nice video with a lot of information. This is an overall, an aerial view of the farm. This is the UGV navigating. This is twice the real velocity. Doing waypoint inspection, you had up there the waypoint. So you go in a corridor, then you turn here at the end of the solar panels, and now you turn right and you go to the other corridor. When you do the turn here, you probably saw that the manipulator that was extended to do the inspection on the right side of the robot was put to its own position, and now it was deployed to see on the left. So we keep doing this also automatically. Everything is autonomous, the navigation. There are points where the robot stops, approaches the panel, and does an observation using camera. I will speed up because my time is almost over, and I still have another thing to show you. Then the map being built here by the JCAL. You can see the map growing and the location of the robot here. So this is a SLAM algorithm, actually loam that we have used. It's a graph SLAM algorithm, so we can actually show it in being built in real time, but essentially we used to pick up all the data and do an offline batch map. Now you can navigate in the map, and now you can localize using the map. And that's what I was saying. You can see here that the red localization is closer, if you trust me, to the real location of the robot. We don't have ground truth. And it's obtained by doing the matching of the point clouds with the map, while the blue one was only with GPS, odometry, and IMU. Well, we also did waypoint navigation with JCal, and then we did the autonomous landing on the UGV using an artificial marker on the top of the robot, in fact, 3 Arucos codes, both with the robot moving like here and stopped. Stopped is easier, of course. Indeed, this was on the site, but we did at IST after this some tests where we improved the algorithm, not only to be smoother, but also such that you can see here the Arucos being tracked. There's 3 of them, so it's more robust, but also allows us to check, and we can change the orientation of the UAV when the UGV turns. In this case, we are not landing, we are just keeping a given reference height, also with some wind and compensating for the perturbations. And then we did with Seville also tracking the robot, but now not using vision, but communications that tell to the UAV the set points, the waypoints of the UGV. And last but not least, we did a teleoperation from France using a virtual cockpit developed by our STA colleagues, both to do to guide the robot remotely using a gamepad, but also to send waypoints to the robot so that it would follow the waypoints. This is the relatively long slide on conclusions because there's a few videos I want to show parts of to you. We have demonstrated the multi-purpose UGVs on different application scenarios, but we have been doing this with other robot competitions where we went from the competitions to real life scenarios. This one, for instance, is an European competition, that's the Rockin project competition, in 2015 in a home. So it actually has a lot of inspiration, assumedly, from RoboCup at home. And but here we were repeating the tasks several times and also the functionalities corresponding to the tasks in order to benchmark the robot. What you see here, sound, is a task where the robot listens to an old lady that is kind of locked in her bed in her bedroom, and tells the robot to go and pick up objects or switch on lights or to put up and down blinders, which are automated home devices which are networked with the robot wirelessly. And then the robot does navigation, grasping, recognizing speech, communicating with home automation devices, all flawlessly and using and autonomously. We also did in RoboCut at home in 2018 in Montreal a very nice run. Unfortunately, I don't have time to show it all, but this robot that you have been watching is a robot that we developed in an European project we coordinated to interact with children in hospitals. The robot did not have an arm because it only had to, do motions with the arm in order to entertain the kids, as you can see, of interaction like the LEDs to show expressions in the face and so on. We added several other things to the robot, like microphones to detect the direction of speech, microphones to understand speech, speakers to speak to the people. And then here it could do several different things. It could navigate inside, could track a person, not be spoiled by perturbations like person passing in between the followed person and the robot. Maybe the guy here is from Brazil. I'm not sure. And Brazil has some successful teams in RoboCup. Then the robot had to pick up a bag that was given to it by the human, and then it would bring the bag in a very challenging place. You can see the team there very excited because the robot had to navigate in a place with a much worse map, and it could have objects not detected by the LiDAR, but detected by an RGBD camera located here, them in his navigation and obstacle avoidance. It did it quite well. You see the head moving always in the direction where the robot is going to move next, exactly to see if there are obstacles down there. So it's not just random. And then it also showed a nice thing that here at some point it had troubles with localization. It tried to enter back the room through the wall, but at some point relocalized itself, and then it could enter the door. Just one final thing, and I'll stop. It's while these were in competition, this is a real world scenario. Robot is interacting with autistic children in experiments in hospital. These test pilots used to be done with people only, a therapist and the children with the parents of the children attending. And the therapist would be doing games with the robot. You can see these balls, these spheres here are part of a game that the child is encouraged to go pick up the spheres and then put them in this case in the belly of the robot. There's also a puzzle to be completed that the robot helps the kid with. We had these RGBD cameras in the ceiling to detect the location of the kid all the time. And the robot looks at it because it communicates with the cameras and knows where it is. Initially, this was done in a Wizard of Oz type of thing. So we were in a room that the kid could not see us, controlling the robot and adjusting it as we were learning the best way of doing it. But slowly, we added more and more autonomy and what you see. And so you see, you don't hear, but the robot is talking to the kid. It's encouraging it. It's showing faces that encourages it. I don't have time to show everything, but I'll show you one that I like particularly, which is when the robot comes to this room to end up the puzzle with the kid. And when it comes, it sees that it cannot enter the room. It says, oops. And at some point, it shows a sad face and it asks for help to the kid, because it cannot enter the room and it wants the kid to do something to let it enter. So you see the sad face. And with the help of the therapist, which has a microphone that we also can hear, so that we know the context where we are, and she can also talk to the kid. The kid is encouraged to remove the obstacle with the help of the therapist, and the robot can finally be happy and navigate inside. So this robot was very similar to the previous one we used in the competitions, and we used a lot of the things from the competitions in the robot. Final slides. We are now doing a lot of things which on the top of this brings the formalization I told you about in the beginning. For instance, we developed recently a PetriNet toolbox for analysis using stochastic PetriNets of plans, and also that we can then pass directly to ROS code and execute the plans, the optimal plans. And we have PhDs running, which are formalizing solutions, particularly of the outdoor robots. One of them is on cooperative situational awareness, and the other one is on cooperative surveillance. And of course, we intend to continue participating in competitions. We plan to go to RoboCup 2023 in Bordeaux and do our best there. Sorry that I went a little bit over bounds. Maybe I don't have much time for questions, but at least it was 1 hour, and I'll stop here. And if you want to know more about our group, you can scan this QR code. And I acknowledge the members of the 2 other projects. Soccer Rob at Home, it's our RoboCup side teams. Inside was the project of the robot in the hospital.
Thank you very much, Professor. Very nice and interesting presentation. Do we have time, bro?
I think I have time for 1 or 2 questions.
So if the audience has any question, there anyone? So, se você quiser que eu traduza, quiser perguntar em inglês.
First of all, congratulations, Pedro, for your work. So I would like to know about the first project regarding the brake pickup. Had you considered the use of another kind of depth estimation because of the problem we had with the RGBD sensor?
Well, as usual in these things, we have a lot of ideas, then we can only concretize some of them because of lack of time for everything. But I think this one would still work fine if we had more time to fine tune it. The major problem was that we would detect the full rectangle of the metallic plate and then take the center of mass of it, which was a bit, we did not have time for more, and it was working fine in indoor environments. And so if we could not fill the rectangle, the center of mass would be shifted to one of the directions, of course, and then it would have trouble. But I think what we should really do was to increase the sophistication of the brick detection. It should not be too difficult, given that it had well-known sizes and colors, to recognize them and especially to locate their center of mass, even without just on the metallic part. I think that was our drawback.
Any others? Oh, okay, I have one. I think can you hear me, Professor? It's okay.
I can. There's sometimes a little bit of distortion, but I can hear.
Yeah, okay. We are the same here. Sometimes just your voice just cuts, but it's okay. We can understand all the slides in presentation. I have a specific question about the costs on the surveillance of the power plant. I believe, okay, I know that that's important to have automatic surveillance on power plants, solar panels, but will the maintenance of the robots worth the cost of the maintaining the power plant? Because building the power plants, I know it's expensive, but the solar panels, they have very okay lifetime compared to the robots and the maintenance cost of the robots. So is it worth already, or you are just studying and trying possibilities and not concerning about costs or in this time?
Okay, so very interesting question, because in fact we had a lot of debate about that here. Indeed, in this, I mean, we might be just testing ideas, as it so happens in many research academic industry. This type of program, in fact, wanted us to go as far as we could to show technology that could be used in practice with an advantage. And in fact, part of the project was also to organize workshops, B2B meetings, and so on with companies and other stakeholders, so that companies that develop technology and end users, like the power companies, in order to in one hand show them that this is being done and they can in the future, the other hand to listen from them about how realistic it is to use these things. Of course, when we started, we had already companies we thought that this might be useful. And what happens, concretely answering your question, in the solar farms is that if the solar, particularly for large solar farms, if we can in the future have this goal of having a fleet of UAVs and UJVs flying, I mean, in time they go out, they start flying, they do inspection, and they go back again recharging. And particularly the UGVs, because the UAVs, to do the inspection of a large farm, will need to recharge along the way in the UGVs from time to time, right? This is kind of not so sci-fi anymore. Of course, dependability is a problem and reliability. But this, from what the company said, would be interesting for them, because very often these places, and even the one where we were, which was a relatively small power photovoltaic farm, these are places usually where people, if they can, they don't want to go there very often to do, except for doing maintenance or so on. Because in this case, for instance, it's quite hot there. It's in the south of Portugal, in one of the hottest parts. Actually, when we did these tests, it was quite hot and it was a problem. And it's close to a city, but still the people aren't usually there. The technicians, they in a while only. And so if these things can at some point become better and more dependable and reliable, they will bring added value. And in fact, there are already robots being used, some of them in more constrained situations, some of them teleoperated for this kind of things. Also for washing the solar panels, for cleaning them. And so looks like this is the way to go. I mean, even a few days ago, I got a link to a conference on WIDEX from these kind of companies talking exactly about the usage of autonomous robots on inspection of solar farms.
Thanks, Professor. We have another question.
How many people do we have there? I'm curious. I have no idea.
Can you turn the camera? So also can see the audience.
About 30,
30, I think.
something like that.
Not a lot. Big auditorium, yeah.
Hello, Professor. I saw that you and your research group used like a generalized robotics platform that has been sometimes like slightly or heavily modified to perform different tasks in different competitions. What is your opinion on using these more general purpose robots rather than like specifically designed robots for cost effectiveness on performing these tasks, for example, like the solar panel surveillance?
Well, it's a difficult question also because it addresses my main point, right? Which I looked at, I must confess, more from opposite to the previous answer, more from an academic viewpoint. I think that in the future, if we want the robots to be effective, at least, I mean, the first thing that comes to my mind is a domestic robot, which ideally would perform a lot of tasks. We have specialized robots for doing vacuum cleaning, right? But if we could have a robot to do that plus other things, it would be great. I cannot, also because I cannot predict the future and see what kind of robot that will exactly be. But I don't know if that will be cost effective comparing to having several robots for each of the functions. I would say in this example, they might be. But in general, direction is interesting because of what I said in the beginning. And it's a hot topic these days. I mean, there's even an European project where we are involved that it's trying to go in this direction, which is if you are capable of developing modules, both the functional design and then the implementation in software, that you can take from application to application, from robot to robot. This is very important, and we don't have that in robotics yet. I mean, we have something close to that, like ROS, not really that. It's not standard. It's not. It was a big step ahead, but lacks a lot of these features. And the robots, which are multi-purpose, push us to develop these kind of things.
Yes. I think also probably like more customized robots pose difficulty in acquiring like models and control systems that can be like easily implemented, like with.
And also, there's one catch with respect to your question, which is, of course, here we have used the robots that we built and adapted them to be multi-purpose, but particularly the ATRV with the manipulator. But I mean, imagine you are in a company, you find that this has some advantage, this multi-purposeness, and you build a robot which is modular, but of course, which is designed, say, to be a domestic robot, not for something else, which can ironing, do the bed, vacuum cleaning, putting things in the washing machines. And this would be designed on purpose for that multitask.
Yes, thank you very much.
Do you have another? Do you have time? So, Professor, thank you very much for your presentation. It was a very interesting work. Thanks everyone for the audience here. Thanks again, and you can start closing the presentation because we are out of time, unfortunately.
Yeah. Okay, thanks a lot to everyone, and best wishes for the rest of the conference.
Professor Pedro, você está aí ainda? Oi, Pedro. Não, mas não tem problema.
Não, o som dele tá aberto ainda, tipo.
Deve ter saído.
Good afternoon, everybody. My name is Fernando Gamarra from the Federal University of Maria, and I will be the chair of the session Navigation and Planning 1, the Lars 2022. Thank you for your assistance and for the people that is with us, and also from the people that are following us virtually. So the first paper is going to cite this trajectory deformation, and it's going to be presented virtually by the author Victor Silverco Justo. So I'm going to give the word to Victor.
Hello, good afternoon. Can you hear me?
Yes.
Okay, I'm going to share my screen. Just a second, please. Okay, I'm not allowed to share my screen. Could you help me with that? I think that I need a kind of... Okay.
Are you hearing me, Victor?
Okay, okay.
Yes, do you enter once again?
Okay, could you confirm that you are able to see my slides?
Now it's okay. Now it's okay.
Okay, perfect. Okay, I'm going to start. Thank you very much for the opportunity. Today I'm going to present the paper, Trajectory Deformation Algorithm for Intelligent Vehicles. Okay, first of all, let me start with an introduction. As we know, autonomous vehicles require robust planning algorithms to deal with uncertain environments. It's challenging to plan movements for unexpected traffic scenarios and ensure safety at the same time. So usually it's necessary a replanning step of the initial trajectories and in order to deal with unexpected obstacles. So conventional approaches generate trajectories that do not consider user preferences regarding the safety distance that the autonomous vehicle should keep from the obstacles. In order to solve that complex situation, we propose an alternative that it's about generating new trajectories based on planned trajectories that are already available. We consider signal temporal logic formulas that represent the safety constraint imposed by the user in order to modify the invalid trajectories. The computational cost of our method is less than recalculating the complete trajectory from scratch. It turns out to be more convenient when there are not many violations near the goal region. Okay. After we review related works to the problem that we studied, we realized that classic navigation algorithms, they have been modified to consider the features of road networks and driving rules. We focus in particular in lattice-based planner, which are mainly implemented using two methods. The first method considers state lattices that decompose the environment in a local variable grid. And the second approach considers spatio-temporal lattices with time and velocity dimensions. We also consider temporal logic, because temporal logic has been used to guarantee safety in the motion planning process. In particular, signal temporal logic specifications have been used to express a set of constraints on the input-output behavior of self-driving cars. So in this work, we consider temporal logic to translate the user specification into some constraints that we implement in our motion planning process. So to sum up, the main contribution of the paper is that we combined the signal temporal logic specification with a planner that is based on lattices in order to deform initial trajectories using constraints related to the space between candidate paths in order to respect the user preferences regarding collision avoidance. And secondly, we applied a weighted function to encode user-defined preferences in its parameters, which turned out to be very useful to classify the paths into different categories according to the level the risk level that was associated to each candidate path. And finally, we tested the proposed algorithm using a robot simulator, which is Weebots. Basically, we work on those points. So let me present the problem statement. So the motion planning process for autonomous vehicles usually involves or consider the minimization of objective functions. In this case, we consider the objective function that was codified in equation 1, which considers terminal cost and running costs. So basically, the trajectory deformation problem is about finding solution for the equation presented in equation 2, which is subject to different constraints regarding the free space in which the vehicle moves, or the constraints related to velocity and acceleration. And also, we modeled the motion of the vehicle as a dynamical system. So the objective is to find solution for equation 2, considering the restrictions that I just mentioned. And for that, we take into account temporal logic. In particular, signal temporal logic is used nowadays in order to enhance the motion planning process. So let me present some basic definitions about signal temporal logic. The basic elements in signal temporal logic is an atomic predicate, which can be true or false depending on the conditions presented in equation 3. Usually X represents a time trace signal. In this case, in our context, the signal is the trajectory of the vehicle. And the function f sub x is a real valued evaluation function that provides an abstraction of the continuous signal, which in this case is a trajectory. So some basic definitions related to STL is that it's built upon a specific grammar. In this case, it's presented in equation 4. So basically, this kind of grammar allow us to represent conditions that we want our system to follow or to respect. We have the possibility to establish quantitative semantics and also a Boolean semantics. In the quantitative semantics will be very useful in our work because we use that quantitative semantics, in particular the value of which is called the robustness degree, in order to specify a minimum safe distance to the obstacles. So we consider also a Boolean semantics because, as we can see, there are different Boolean structures that we can consider, but in this case, we just consider the interjection because we know that in a particular situation we or an autonomous vehicle may need to handle different obstacles. So in this case, that represents the intersection, the possibility to deal with different obstacles. So this is the main methodology, or in this slide we can see the flow chart of our approach. We basically start the planning cycle, and the idea is to first generate candidate paths using a conformal lattice planner. And then we start in that way in order to modify in order to get two-dimensional paths considering receding horizon planning strategy. Then the planning cycle starts with the vehicle's initial state. In this case, it's represented with the variable s sub 0 that is used to compute the resolution of the separation between lattices or between candidate paths. The planner starts in low resolution modes, so it generates few candidate paths to handle essential driving situations. For example, in a typical highway scenario, an autonomous vehicle may need just 3 candidate paths. One, in order to follow the current route, and 2 alternative paths in order to make a lane change maneuver, either on the right or on the left. In the next step, we generate multiple candidate paths using which is a variable called the computed resolution and the state of the vehicle at that particular stage. Then the best path among the generated lattices is selected considering the cost function to minimize. After that, the robustness value of the selected path is calculated based on the STL rules that guarantee safety. In this case, the robustness measure of the current lattice and a predefined robustness value are jointly used to calculate a safety indicator value. This safety value is compared with a threshold to decide either to repair the selected path or to include the current path on the final trajectory. And the deformation process occurs only when it's necessary, and it involves determining a cutoff state related to the initial selected path. The cutoff state includes the breaking point that will be used as the starting point for the new candidate paths with safety constraints. Moreover, that cutoff state is used to compute the new resolution of separation between paths with safety constraints. The planner is in high-resolution modes during the deformation process of the initial path. Therefore, the path generator may produce multiple paths aiming to provide enough safety to avoid any possible collision. After that, the selection procedure of the best path is based on the additional constraints related to user preferences. For each new path, the robustness values are calculated and transformed into a gain to influence the selection of a new path from the cutoff point to the goal point. After that, the safety indicator value is calculated to decide either to make a final adjustment of the current path or to continue with the planning cycle. Then the planning cycle continues to the next stage when it's not necessary to repair the generated path. The current path, either the initial path segment or the repaired path segment, is combined with the path segments that were previously generated in past cycles of the planning procedure. And finally, it's necessary to determine if the final path that includes all the path segments up to this stage is enough to reach the specified planning horizon. New vehicle states are considered when the final path does not reach the specified limit. These states are used to generate a new path segment, on the other hand, when the planning horizon has been reached. The last step is to form the final trajectory and to finish the planning cycle. So this basically summarizes the procedure in the trajectory deformation methodology that we consider. We can specify more about this. For example, here we consider this in equation 8, this expression allow us to specify the minimum distance that we wish to accomplish in the motion generation process. So we specify.
Sorry, interruption. Yes, to remember you, we have 10 minutes for every presentation.
Okay, thank you. I'm just in the last part. So basically, we specified a weight function that I mentioned, and we introduced some parameters to that help us to classify the candidate paths according to the risk level that are associated with them. So we specify this weight function that is introduced in the cost function that allow us to classify the paths as in this slide. So in this case, we can see that candidate paths that are in blue represent the most risky paths, and the ones that are in green indicate the safest paths. So with our approach, we are able to classify the paths according to the risk level. And we can see how it works in simulation. Let me show you a video here. So in this case, the autonomous vehicle is able to avoid some obstacles on the road. But basically, the idea is that we were able to avoid excessive oscillations that are characteristic of the conformal lattice planning approach. And the evaluation shows that we were able to reduce the computation time, considering the deformation of the initial paths, instead of replanning and generating new trajectories. And here we can appreciate this, that we are able to generate, we are able to increase the resolution according to the situation. So initially we have 3 paths, but if necessary, we can generate more paths that allow us to get a safe distance to the obstacles, but avoiding to be so far away of the obstacles. And basically that's what we propose in the paper. So we combine the STL specifications related to safety with a conformal lattice planner. And then we compare that with a conventional lattice planner in order to see how it works, and if we were able to see that it's possible to reduce the computation time. And basically that the deformation of the candidate path is based on the STL robustness value that help us to understand how dangerous it is to follow a selected path. And that's all that I have to say. If you have any question, I'm happy to answer.
Do you have any questions? Okay, if you don't have any questions, just question, because how do you plan to optimize in some way those trajectories that are generated by your algorithm?
Basically, since we use as the conformal lattice planner as the base, the method to generate the trajectories, so those trajectories are optimized But the idea was to adjust the quantity of the candidate paths according to different situations, so that we can't avoid excessive oscillations, because that's a problem of the conformal lattice planner. We can generate many lattices, but maybe it's not necessary to have all of them since the beginning. So as in this figure, we can see that we start with only 3 paths, but then we are able to generate more paths that are in green, so that we can get a safe distance to the obstacle, but we can avoid being so far of the obstacles. But those paths are optimized. That's because we consider the conformal lattice planner, which optimize the paths in the generation process.
Okay, Victor, thank you very much for your work, and congratulations also for your work. We are going to the next presentation.
Okay, thank you very much.
Thank you. Thanks to you. Start UHV and UAV path planning for inventory management in warehouses. The presenter, collaborative. It's from the University of Minas Gerais. We have the author Caio Ribeiro, Leonardo dos Santos, Douglas Guimarães. I don't know who is going to be the presenter.
I can present, but I need to have the permission.
Okay, so the presentation will be virtual. Please try to give the presentation, and this indication is for all the other presenters, just in 10 minutes, please. Caio, you can present.
Hello, can you hear me?
Yes, I can hear you.
Okay. Hello, I'm Caio from FMG Brazil, and I will talk about our work entitled Collaborative UGV UAV Path Planning for Inventory Management in Warehouses. Path planning is a crucial step in mobile robot automation, and with the increase of interest in collaborative systems, new techniques have arisen. The goal of cooperative path planning is to obtain a path for all vehicles in the system, which often depends on each other. Multi-robot systems can be separated into homogeneous, where there are several robots of the same type, and heterogeneous, where there are robots that are not the same type. Our work focuses on the heterogeneous one, especially the aerial and terrestrial cooperation. The use of robots in warehouses is a reality. Robots can be used to carry items and do inspections, although non-heterogeneous systems were found to be proposed in this environment. Our work presents a possible solution for the following question: how to plan a path for both robots in a cooperative UAV-UGV system that would take full advantage of team capabilities for visiting shelves in a warehouse. Below, we can see an illustration of a solution that we'll talk about later. First, we model the cooperative system that our problem will take place. The UGV will carry the UAV. The UGV goes through the warehouse. It will stop in one point. Then the UAV will fly and visit shelves nearby. The UAV goes back to the UGV, and if the path is not finished, it continues this flowchart until the path is completely finished. Given this scenario, the work's objective is to develop a strategy capable of planning paths for both robots in a way to maximize the total number of shelves visited. Related works about the use of robots in warehouses lack the use of heterogeneous multi-robot systems, consisting only in single robots or homogeneous multi-robots. However, the cooperative path planning for UAV-UGV is well studied. Our work tries to innovate considering a different situation than those works before. The literature considers that the budget, or energy, or battery, for both robots are enough to complete the whole mission. That can be done by recharging the batteries or considering an unlimited amount of energy. Our work considers the scenario where both robots have a limited budget that is not necessarily sufficient to complete the whole mission, and that is in our case, to visit all the shelves. In that sense, instead of using the least energy possible, we would like to use all energy at our disposal to visit as many shelves as possible. Our formulation will then consider a limited budget for UAV UGV. UAV will not recharge, and we want to maximize the rewards. The problem of maximization with a limited budget can be classified as an OP, an optimization problem, or a Turing problem. This is the strongest point of this work, the formulation of the collaborative problem using the OP. We formulate it by two combined OPs, the UGV OP and the UAV OP. The UGV OP is for where the UGV should stop in the warehouse, and the UAV OP will tell which shelves the UAV should visit at every stop. This type of formulation was not explored in past studies. This we have an example of a final result. Then we propose a way to solve these two combined OPs. Note that the formulation as a double OP is the greatest achievement of this work. We propose solutions to the OPs for evaluation of the formulation. It's not the best way to solve it. For have the best way to solve it, it will be work for future works. The UAV OP is solved using a grid strategy and a local budget restriction for each flight, so the drone does not go too far away from the starting point. The algorithm searches for shelves in the neighborhoods and visits the one with the most rewards. This will continue until the UAV uses the whole local budget, or if there are no shelves with rewards in the neighborhoods. This way, in every stop, a sequence of shelves to be visited is predefined, but the sequence will change based on the UGV OP. The UGV OP is solved using genetic algorithm. The population is made by individuals that represent a solution, a path. Every path has their fitness as being the total sum of shelves visited in that path. Solutions that pass the UGV budget are corrected to be valid. And finally, for every UGV path, the UAV predefined path is corrected, so shelves are not being visited more than one time. The complete path is generated by the union of both strategies. The shelves to be visited by the UAV in each stop is the solution from the UAV OP modified to not have repetition or to not run out of the UAV budget. The path and stops to be done by the UGV depends on the fitness that is directly related to the number of shelves visited in each stop of the UAV OP solution. This strategy was implemented in Python and several experiments were made. The following solution demonstrates the convergence of the GA, and it's notable that the number of shelves being visited rises with the generations. The solution found considers point 1 as being the starting point, point 6 as the finishing point. The red squares are shelves that we desire to visit, black squares, the ones we don't want to visit. The path realized by the UGV carrying the UAV is shown in the blue arrows. The red dots are stops made by this system, UGV carrying UAV. The red arrows shows the path being made by the UAV at every stop. It's notable that in this illustrative example, in every stop, at least 2 shelves are being visited, with the exception of the last one, which is set. In a bigger environment, it's notable that the UGV goes very far into the warehouse to make stop points where the UAV can visit several shelves in one stop. A similar result is analyzed in this complex scenario. In every stop, again, several shelves are being visited. With that, we can analyze that the solutions are actually working properly. as the stops are being made in places where we can visit several shelves, so the final path will visit a good amount of shelves. The main contributions of this work is that we formulated the warehouse management problem as an OP. We solve the formulated OP using generic and greedy algorithms. We take advantage of the capabilities of a heterogeneous team, and we apply a heterogeneous cooperative system into a warehouse environment. In future work, we intend to consider the time the UGV spends at each stop. We want to allow the vehicles to move simultaneously, and we want teams composed by more than 2 robots. Thank you. Any questions?
Okay, thank you very much, Caio, and congratulations for your presentation. Somebody has a question for Caio? Hi, Caio, can you hear me?
Yes, I can.
Okay, so Caio, congratulations for your work. Very interesting. I'm wondering, do you have any partnership in which
any partner? Sorry?
Just a second. I think I have to be in front of the microphone so you can hear me well.
Yeah, that's better.
Do you have any kind of partnership in which you can test your system in real scenarios? Thank you.
I'm working with the Verlab, then maybe we can try to do actually real work scenarios, but not yet.
Okay, thank you, Victor. It's a very interesting paper. Now that we know from some statistics that Amazon is investing in this area of warehouses in robotics, and nowadays it has more or less 100,000 robots that are used in warehouses. Yes, a little question. I do not know if you remember how do you code the chromosomes in your genetic algorithm?
Yes. How we code?
Yes. What were the
okay
that have you coded the chromosomes?
Okay, the chromosomes in the genetic algorithms are a little bit complex, but they are a Python list with several attributes. I don't know if that explains too much or not. And hello?
Yes.
And in the list, we have the genes that they store the stops being made and the shelves being visited. They have the whole scenario in one gene.
Okay, can you use the fitness function as the number that it visited the shelters, right?
I don't think I can hear you very well.
The fitness function was the number of times that it visited one shelf, right?
The fitness function is the amount of shelves being visited by one path. So in this case, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The fitness have the value of 12 in this path.
Okay. Perfect. Well, thank you very much, Caio, for your presentation. And we are going to the next presentation. Its title is Autonomous Robot Navigation in Crowds. And the author is Paulo Afonso. Okay. I'm going to give the word with Professor Paulo Ferreira.
Thank you. Thank you, everybody. I will present you the work of my PhD student, Paulo, and it is a literature review about autonomous robot navigation in crowd. Oops. This is the summary of our presentation. Our presentation today, a brief introduction, the two kinds of methods we identify in the literature, brief discussion, also brief discussion. Autonomous navigation in grounds is a very challenging area nowadays. The robot must navigate in scenarios, in environments like airports, museums, malls. And we are interested in this scenario because we are working in motorized wheelchairs. And the idea is that these wheelchairs in airports will navigate autonomously and bring the person to the gate, to the right gate, autonomously. This is our challenge. And we are studying the approach in the literature that allows robots to autonomous navigate in this kind of environment. So it's a very challenging task because the movement of the people can generate obstructions in the scenario. It's a very random movement. If you are in a mall, for example, people are changing direction, people are talking and disperse the group, and this movement obstructs the path of the robot. There is uncertainty of the human behavior, and it can lead to unsafe situations for the robots and for the people. There's also a sensing problem for collision avoidance because of the light of the environment and how fast it changes its state, and the perception of the robot where it is at each moment is very difficult to achieve. So we searched in the literature the last 7 years, the most important scientific journals and conferences, like IRIS. We searched for 10 keywords: autonomous navigation, crowded scenarios, crowded navigation, collision avoidance in crowd, robot navigation in crowd. So we search for these keywords in the literature, and we find lots of papers, and we choose the most pregnant ones, try to identify the state of the art. And we also get, for each paper, we select the reference of these papers and search again. So it was a very intense work to looking for all the proposed approach until now. These analyses were conducted in these articles, and we found two kinds of methods, and we divided, splitting reactive methods and predictive methods. The reactive methods is the ones that the decision-making process of the agents starts when there is an imminent collision. If the robot will collide, it starts the decision process where to go. And in the predictive methods, the idea is to find paths free of collisions, which you can imagine is very hard. So we can split the literature in these two kind of methods. In the reactive methods, we found lots of methods based in reinforcement learning, where the robots are rewarded by when a good decision is taken, when the collision is avoided. So it's a original, it's a common reinforcement learning based. There's several in the literature. There's the ones based on deep reinforcement learning based, which uses deep learning in the process, neural networks are inside of the algorithm to the idea is to do not use only the matrix, Q matrix to a real world. So there is a neural network to compute the real world. There is another set of relative methods based on artificial potential field, which is a common approach in the navigation methods. We can find ones that adopted and create a new attractive force points and help the moving robot to escape from the local minimum, and some modifications of the repulsion field function, introducing a relative distance between the target point and the robot. So are modifications in the artificial potential field technique that allows the robot deals with route. There's another set of reactive methods based on velocity obstacle, and there are lots of velocity obstacle, reciprocal velocity obstacle, hybrid reciprocal velocity obstacle, and a huge set of this kind of methods that starts in 1998 that allows to navigate in crowds. The robots navigating crowds. And the predictive methods that the ones we try to build a path prevision. There one very interesting one that is the trajectory prediction, where some solutions use agent-based methods to predict the pedestrian trajectories using the velocity space reasoning. So that there's a lot of computing predicting the action of the humans, basically models. The agent should be able to learn the interaction model for the trajectory data or a human or a real human being. The idea is to avoid the most dense areas. So you choose a less crowded path. And there's another set of approaches based on human behavior. The idea is to learn models capturing the human behavior when walking in this kind of scenarios and try to adapt a plan based on this kind of human navigation. We can see here that this kind of every approach uses mixed with another kind of approach, and every new paper tries to find an improvement, mixing and mixing previously presented approaches. We can see that among our selected papers, 55% of these studies adopt the reactive approach, which is more 50-50 and reactive and predictive. But we can see now that in the last years, a significant rise in the learning-based techniques, using learn to make decisions in 61% of the selected studies. And this analysis results also reveal that there is a significant increase in the proposition of students that studies that focus on social navigation in crowded environments. Social navigation is a relatively new approach, which is considering how to navigate with interacting with people, respecting the social behavior of one person. We can say that there's a group of person talking, and we cannot cross through the group. We need to turn around. So even there is a space you can go through. Using social navigation, you need to turn around and do not cross the group. So it's social navigation. Concluding, therefore, for autonomous navigation, dynamic and crowded environments, we can find three essential points that we must observe in the future of our work. the need for collision prevention policy through reactive or predictive behavior, or even mixing both, the ability to properly calculate a variable trajectory and change this trajectory dynamically. And it's very important to change dynamically as the crowd moves. And the ability to identify people to improve decision making. So you need to know which obstacle is person or another object. It's really hard, but it's really important to dynamically take decisions. That's it. Thank you.
Thank you very much, Paulo. Congratulations for the work. And do you have any questions? Somebody? How many real questions?
Lots of simulated ones. Simulated. We found one study that they tried to use in a mall, the robot, but it's always complicated because the people inside do not behave normally when we put a robot in this scenario. People goes to the robot to see what's happening, go off the robot, taking distance from the robot. So the most difficult part reported in these studies about to use it to experiment it on a real environment is that people do not behave normally when we put the robot in a mall, for example. They put the robot in a mall and report that it's not possible to try because everybody goes to the robot or go into the robot. So it's really hard to try in crowded environments. We expected that our wheelchair will be, how can I say in English? Will hide that it's a robot, a wheelchair. So people will behave normally because it's a wheelchair. But it will be a robot navigating autonomously.
Thank you. Have you, it's a small question, have you think about a probable scenario which we are going to apply this methods, predictive or design, making some experiment, in simulation or real world, what we choose projection or planet to use?
We start with a real robot, but the pandemic situation, we go to the simulation. But we are working mixing both because we are working in airport scenario. So we have the path planned to the gates. If you are in this position, you want to go to the gate 12, we know the path to this gate. So we will mix this kind of planning with reaction, trying to react, changing the direction if something happens unexpected. So our scenario is the airport, and we have the wheelchair, and we tend to experiment in this real scenario. But if you think a robot that there is a person inside, there's a lot of another issues that we need to take care, because this kind of wheelchair cannot change direction so quickly like this wheelchair, because the person inside, the human inside, it's not normal. So there are lots of things to put over the planning and reaction, because there's a human side of this kind of this robot.
Thank you, Paulo, and congratulations once again for the work. And we are going for our last presentation. Its title is going to be, a standalone obstacle avoidance controller for image-based navigation. And it's going to be presented by Adri. Yeah, please. Thank you very much. Good afternoon, everyone. So my name is Adrien Durand-Pustelville. I am professor at the Universidade Federal de Pernambuco. And I present the work Standalone Obstacle Avoidance Controller for Image-Based Navigation. It's the result of a collaboration with Vivian Canard and Thierry Santenac from the last CNRS in Toulouse. So our goal is to design image-based navigation framework to control a differential robot with a camera embedded on a band platform. So we have to control 3 degrees of freedom, 2 of the band base and 1 of the band platform. And the robot is also equipped with a laser rangefinder to detect the obstacle. So to drive the robot towards the goal, we use an image-based visual sampling, which is a reactive approach. And to do that, we define the task in the image space. So the goal, here we have an example, is to extract visual features from the scene and make them converge to their desired value, which correspond to the goal. So in a free space, it works really well. The issue usually is that it's very difficult to take into account obstacles, constraints with standard control. So, relating to the implementation, when we think about reactive approaches dealing with obstacles, we might think of position fields, a bit of histogram, diagonal approach, velocity obstacles. So the thing with all those approaches that they compute both the navigation and the obstacle avoidance in the metric space. So in our case, we want to do the navigation part in the image space, so it's not obvious to use them. There exists one work where they adapt the vector field histogram to the specific case of the line following in the image space. So another issue is to increase the image-based visual sampling by using, for example, optical-based approaches, grid-based approach, or to project free cells in the image space and to define a second task to achieve. A last solution is visual predictive control, which is the fusion of predictive control with visual sampling. And in the optimization program, we can include constraints regarding obstacles. This is what we are working. Today, the goal is to define a simple solution, a standalone obstacle avoidance controller. So a controller that will avoid obstacles by itself. And the idea is that today we are using it with a controller, but it could be used with a position-based controller, it could be used with a GPS-based controller, so this is not important. It has to work by itself. And then we combine it with the navigation controller within a behavior-based navigation framework. In this work, we use a mid-state machine to combine the 2 controllers and decide based on the situation which one should be. So the obstacle avoidance controller is based on the spiral model. So if we consider a mobile robot, here it's the OR with velocity vector V. And then we consider a point, OS, and within the robot frame, these points polar coordinates are distance D and angle alpha. And if we have a constant linear velocity V and the angle alpha is constant, the robot will describe a spiral. And in that case, you will have following equation of the distance evolution. What we can see is that the shape of the spiral depends on only one parameter, alpha. And so we will have an outward spiral. So the robot will move away from the center
And in one spiral, we're going to do 2 at the center. And when it's equal to plus or minus pi over 2, we describe a circle. So which is interesting here, with just one parameter alpha, we can control the evolution of distance. So from that model, our goal is to design an obstacle avoidance control. So first, we have to define the center of the spiral. So we have one point to represent the whole obstacle. So that point must be representative of the R. This will be the first change. And the second thing, so to define a spiral to travel, we have the center. We need also to define a reference spiral angle. And so we have seen that with this alpha, we can form the distance. So we have to choose an alpha angle that will prevent the robot from colliding with the obstacle. So one thing here is we are not trying to follow one specific spiral. We won't compute one spiral and try to track it. The thing is that at each iteration, for each new data, we will compute a new spiral to track. And each iteration will track the spiral. For the robot, we are not expecting the robot to discontinue. We have a path that looks like a spiral, but we will use the spiral model to avoid the obstacle. So two things. First, we have to compute the center. So what we do, we receive one cloud from the laser tracker. We divide it to form subsets, one for each obstacles. We might also merge some obstacles if we consider they are too close from each other and that the robot will pass between them. And so from those subset points, we select the closest one to the robot. So now the most obvious solution is to say in that subset point, I will select the closest one, here it's OC, because it's the most dangerous point of the obstacle. So I'm going to use that point as the center of the spiral. So this works pretty well, but what will happen is that the robot will describe a path that has the same shape as the obstacle. So it works well when we consider the complex obstacles, but if we consider non-complex obstacles, in that case, it might be interesting to close the concavity and use as the center of the spiral the closest point on that line segment to the. So here, which is important, is that we have already decided that the point cloud we are considering represents one of the blocks the robot can pass through. So closing the cavities won't be an issue. So we have the center of the spiral. Now we have to select. So if we use a constant angle value, we won't be able to control the distance. The distance will stay constant, will decrease, but we don't control the initial value of the distance. So we need to use a time varying angle. So basically, here is that when the current distance is larger than the desired one, the robot will have to drive towards the center to reach the desired value. It's the opposite when it's too close from the obstacles, it has to drive away. And when it's at the right distance, we want the robot to stay at that distance. So we have a time varying reference angle made of 2 parts. The first part is alpha c, it's equal to plus or minus pi over 2, depending on the direction. And so that parameter, that part, will keep the robot at the same distance from the obstacle. And the second part, alpha v epsilon, it's used to adjust distance. So we will be driving too long for obstacles, away from the obstacles. And important, it will be equal to 0 when the robot is desired distance. So now we have a center, we have a reference angle, we need control to actually track the spiral. So the approach to design the controller is very similar to what we do in the visual theory or task function approach. So we define the raw current angle minus the desired time varying angle. we impose an exponential decrease, so it's equation 4. Then we compute the derivative of the zero. By combining equation 3, 4, 5, we obtain the controller described in equation 6. So we consider constant linear velocity during the time interval. So it could be computed by another process, or we can decide. Then we have this controller to control the orientation of the database. And finally, we have a third degree of freedom. Here, we control the band platform in order to keep the landmark in the field of view of the camera. Right now, we are not using vision to. Once the obstacle is void, we have to switch back to the visual circle. So we need to see the landmark of the text. So we control the band platform to keep the landmark in the view. So we have two controllers, one to drive the robot to one goal, the visual one is to avoid the spiral. And so we put them in a fixed state machine here, so we have the transition. So the one thing here is we have two states for visual sampling, two states for obstacle avoidance. It's just to prevent the system from switching back and forth for visual sampling. I happen because it's very difficult to find relevant condition transition just based on current data. So we have used that solution. So here it's a video simulation obtained with Lars. So we have a couple of speakers. We can see the top right bar is the visual summary, that is the processing. So initially here, the robot considered the obstacle as dangerous. So it's doing the spiral for it. So you can see it's not actually describing the spiral, it's following the shape. And by using the obstacles, here we consider that the wall and the cubes belong to the same obstacle because it considers cannot pass through based on the practical reality. And once the obstacles do not represent the picture anymore, we will switch to visual to finish the visual. So here it was interesting because of the L-shaped obstacle at the beginning. Also was able to pass through the gate. Here's another example where we have chairs length. So without using all the obstacles, every leg of the furniture we consider the different obstacles. Here everything is merged, is considered as one obstacle. And despite all those gaps between the obstacles, managed to circumvent the obstacle. Once the table is not dangerous, it drives towards desire. So, in this approach, the idea was to design behavior-based navigation solutions. So on one side, we have visual survey control to drive the robot towards the goal. On the other side, we have a spiral following controller to avoid obstacles. That spiral following that obstacle avoidance controller managed to deal with convex, not convex obstacles. The one thing is that the obstacle avoidance controller can be used. So here it's an IDS whatever space. So that's the point of using the standalone. And finally, we put everything together to select the appropriate situation. So three things we are currently working on. We want to add a third layer to anticipate the obstacles and try to follow less the shape of the
to define better transition. So we will have to have 2 states per controller. And the idea here is to use prediction to predict transitions, so we will have more relevant transition. And finally, something we are going to work on, actually, consider dynamic obstacles. And the main difference with what I'm showing here is that we won't try to control the distance. We will just delay the challenge is more to get what static, what's dynamic, which direction to try to. So thank you very much for your attention. Thank you very much for the presentation. Andrew, somebody has any question? Somebody? Yes, they have a question. I don't know if you consider, because image-based spatial survey is nice information. You can avoid those model. If you would inventor would apply position-based spatial survey, this will also be adapted to position-based spatial survey. Yes, yes, that's exactly the point of designing standalone control. So in the finished fashion, I will substitute the IDBS with the PBBS, and the rest of the work is that was the point to have really a standalone, to adapt, increase existing. Yes. Okay. Thank you very much for the presentation once again, and congratulations for the work. Thank you. And we are going to close this session.
Próxima sessão.
Good afternoon. Nice to meet all of you again. So nice to be here. We are going to start a new section now. It is the AAV1 area in class BI equals 1. And I would like to invite the first presenter that will present for us the real-time INSDFPS vision applied to the navigation of autonomous underwater vehicles. Luis Souza, Leandro Frutuoso, Daniela Silva, and Vitória de Barros. So, Mike. We don't hear you.
Can you listen to me?
Yes, now it's fine.
Okay. So, can I start the presentation?
Go ahead, please.
Okay. Good afternoon. My name is Adriano Frutuoso. The first author is Mr. Luis Souza. And this work is the real-time INS-DVLPS fusion applied to the navigation of autonomous underwater vehicles. So, introduction. Autonomous underwater vehicle is an unmanned mobile robot used in a variety of ocean and inland water applications. So the applications in areas of military, scientific, and commercial areas. Some examples of applications of AUV is in oceanography research, maintenance of ocean installations, exploration and monitoring of riverbeds, and underwater mining detection. This is some examples of applications of unmanned, of autonomous underwater vehicles. So the navigation systems of the AUV provide the velocity, position, and attitude of the vehicle. For it, commonly AUV navigation sensors are the GNSS receiver, the acoustic markers, the inertial sensors, Doppler velocity log, pressure sensors, attitude and head reference systems, and electronic compass. These sensors are commonly employed in AUV navigation systems. So in this figure, we have the AUV Pirajuba, a photo of the AUV Pirajuba. AUV Pirajuba is a AUV developed by the team of the Unmanned Vehicle Laboratory, the LVNT of the University of São Paulo. So Pirajuba is equipped with these sensors: IMU, pressure sensor, Doppler velocity log, GNSS receiver, electronic compass, and a low-cost attitude and heading reference systems. So IMU, the inertial measurement unit, is employed in conjunction with onboard auxiliary sensors. The auxiliary sensors can be the GNSS receiver, the pressure sensor, and the Doppler velocity log. These sensors are commonly employed with auxiliary sensors. The integration of the information between the IMU and the auxiliary sensors is performed by the common filter. The common filter is the common method to perform the sensory fusion between the IMU and the auxiliary sensors. So, however, the difficulty of using the common filter is the tuning of the process noise covariance and the merger noise covariance matrices. So, in this figure, we can see an example of the incorrect tuning of these matrices in the estimation of the position of the UV. So, in this case, we have a divergence on the estimation of the position of the UV. So, it is an example of the incorrect tuning of these matrices of the common filter. Navigation equations. So to implement the real-time navigation algorithms, we implement some equations, some navigation equations. These equations describes the vehicle velocity of the UV. For example, these equations describe the velocity of the vehicle in the navigation frame. The navigation frame, we use the north, east, and down navigation frame. So this equation describes the attitude, describes the rotation metrics between the body frame and the navigation frame in terms of the parameters of the quaternion. So in this equation, this equation describes the attitude update of the quaternion parameters and the relation between the quaternion parameters and the angular body rate in X, Y, and Z axis of the body vehicle of the body frame. So these equations describes the position of the vehicle relative to Earth's surface. In this case, we have the latitude, longitude, and altitude position in relative to the Earth's surface. Sorry. To perform the common filter, real-time common filter, we implement the state space variable, the state space model of the dynamic error of the AUV. So this equation describes the attitude error of the vehicle. This equation describes the velocity error of the vehicle and the position error the position error mode of the UV is described by these equations that corresponds to the error of the latitude, the error of longitude, the error of altitude of the vehicle. So all these equations are translated into the state space model, and the state space model of the dynamic model of the vehicle are implemented in the real-time navigation algorithm, specifically the real-time common filter. So we implement the 15 order common filter. So for it, the common filter was implemented using a closed loop error state approach. So the equations of the prediction stage are well-known, prediction stage equations. So these equations is the prediction stage of the common filter, and the equations of the correction stage or the update stage, we use the method scalar measurement update or sequential processing. So we use the scalar measurement update as MU or the sequential process to implement the correction stage of the common filter. The equations are given by these expressions. So the common filter, for offline tuning of the common filter, we use a method. We use the metric-based predictive method. This method makes use of the innovation covariance for developing two metrics, in this case, J1 and J2, that evaluate the effect of the process noise and the measurement covariance on the filter. In this case, J1 provides the effect of the measurement noise in the covariance, in the innovation covariance, and J2 measures the effect of the process noise covariance into the measurement on the specific, the sum of these variables, C1 and C2. So for tuning, offline tuning of the common filter, we use the metric-based predictive. We use the metric-based predictive methods for tuning of the metrics of the common filter, specifically the metrics of the process noise covariance metrics. So the focus of these presentations is show some experimental results, simulation and experimental results for the real-time navigation algorithm implemented in the AES-CV. Simulation experimental results. Preliminary field tests were carried out at the Olympic rink of the University of São Paulo using an AES-CV trimaran in this photo. This photo shows the AES-CV trimaran developed by the team of the university, developed by the LVNT laboratory. So this AES-CV is an autonomous surface vehicle. The AES-CV is a Polymer 03. Polymer 03 is equipped with a GNSS receiver, an IMU, an Doppler velocity log, a pressure sensor, and a low-cost altitude and head reference system. So these sensors are the same used in the EUV Pirajuba. So fielding tests were carried out in the Olympic rink of the University of São Paulo using the AES-CV trimaran. So figures 3 and 4 shows the AES-CV trajectory generated by the real-time navigation algorithm, the red line trajectory, and by the GNSS receiver in blue. So this figure shows a comparison between the real-time navigation algorithms implemented in the AES-CV and the GNSS receiver in the blue trajectory. So these results were obtained for a straight line maneuver. This maneuver, the total time duration of this maneuver was around 27 minutes for this experiment. And the velocity of the vehicle was approximately 0.9, 0.8 meters per second. So in this case, in this figure 3, we have the results for an INS DVL-PS navigation type with sensory fusion using the common filter. And in figure 4, we have the same trajectory, straight line maneuver using INS DVL-PS navigation type, but without sensory fusion, like no common filter. In this case, the position errors depicted in the figures 5 and 6, we have the position errors on north, east, and down direction are approximately equals for with and without common filter for this test of the straight line maneuver. So considering the sensory fusion, consider the case of INS DVL-PS navigation time with sensory fusion, the position errors was around 7.5 meters on north direction and 5 meters in east direction. So considering this maneuver, 27 minutes for this maneuver, the distance cover error was around 1% of the distance covered. So, considering the case of INS DVL-PS navigation time without sensor fusion, the position errors was around 10 meters on north direction and 7.5 meters in east direction. So in this case, the position error was approximately equals for both of the both cases. No? For evaluating the trajectory effect on the position errors, figure 7 shows this simulated low-moor maneuver, in figure 7. So the simulation was performed to evaluating the trajectory effect on the position errors. So in figure 8 and figure 9, we have the north, east, and down position errors. In this case, on north direction, the position error was around 5 meters and 7.5 meters in this direction. For the case of INS DVL-PS navigation type with sensor fusion using common filter. So in figure 9, we have the same, we have the position errors for the case of without sensor fusion, without common filter, no common filter. So we can see that the position errors for the case of with sensory fusion using common filter, the position was 5 meters in north direction, maximum 5 meters in north direction, and 7.5 meters in east direction. However, considering the case of without common filter, the position errors was around 10 meters on north direction and 7.5 meters in this direction. So the position errors was smaller considering the case of with common filter, using common filter. So consider the simulated low-moor maneuver, the position errors on north and east direction were lower for the navigation with sensor fusion. In this case, the distance cover error was around 0.06% for the navigation with sensor fusion and 0.22 for the navigation without sensor fusion. So the simulation results suggested for the case of low-moor trajectory, the low-moor trajectory reduced the position drift. Hence, in this case, in future works, we intend to perform experimental tests with long-time low-moor trajectories. And conclusion, according to the experimental results, in this case of a straight line maneuver, the position errors of the navigation systems with sensory and without sensor fusion were approximately equals. But considering, in this case of the simulation suggested, considering the case of low-moor trajectories, the simulation suggests that the low-moor trajectories can reduce the position drift. So, in future works, we intend to perform field tests with long-time low-moor trajectories to evaluate the performance of the navigation systems we compare with the case of with and without Kalman filter for a long time low Moore trajectory. So that is all. A special thanks to CNPq and FAPESP for funding the scholarships and the project. And thanks to the attention. That is all.
Okay, thank you for your presentation. And we are open for questions now. If somebody wants to ask some questions for him. If you don't do it, I have to do. Save me. Okay, so I do have one short question for you. At the title, you talk about UAV. In your presentation, you used a ASV to do the tests. Is this any, I don't know, if you're going to find any difference, mainly the attitude of the position, when you get in deep water, is it going to be working the same way? Can you talk a little bit about that, please?
Yes, the ASV Polymer 03 was developed to use with a platform test. The ASV developed by the LVNT was developed to test and to validate the navigation algorithms for both ASV and both AUV. So the ASV is more suitable to perform some modifications in the navigation algorithms in the field. It's more suitable to implement some modifications in the field. So the ASV facilitate, favor the field tests in the Olympic rink or in the sea, in Ubatuba, for example.
Okay, so it's going to be more or less a straight implementation when you deal with a UAV.
Yes, yes. We have some results for the EUV, but these results is more for water obtaining using the ASV.
Thank you. Do you want to make some more questions to him? Anybody in the internet, the YouTube? Okay, so I thank you very much. Please close to him.
Thanks. Thanks, Patrick.
And now we call our next presenter. The work is a framework for biological control with unmanned aerial vehicles. Is going to be presented by Professor Paulo Ferreira from Universidade Federal de Pelotas, Brazil. Thank you.
Thank you. Hi again. Okay, it's hard to present here. I don't know if I can handle it. Okay, I will try. Can you? Full. Okay, thank you. So I will present to you the work of Bruno, which is my PhD student. He developed this framework for biological control with UAVs. This is the outline of the presentation. I will introduce this. Actually, I will present our motivation to develop this framework. The framework by itself, experiment and results, and conclusion. Our motivation is based on these numbers. Brazil is a world leader in agribusiness, in production of food, the use of poison. Let's talk directly. the use of poison between 2002 and 2012 went from 3 kilos to 7 kilos per hectare. We are eating much more poison as the time goes on. And even with this, lots of poison in our food, about 20% to 40% is lost due the crop pests, even applying pesticides. The biological control in Brazil is increasing in the last 2 years, and we are focusing in this kind of new approach to control the pests in crops. I will talk a little bit more about it because it's important to us understand which is biological control. This is the life cycle of one pest, which is the butterfly fly over there. It's a corn pest. So it puts eggs, the eggs turns in larva in pupa, and pupa in a new adult fly. The biological control is to deploy in the nature wasps like that one, which puts its eggs inside the egg of the fly and parasites that egg, and the fly never borns. That fly is the egg is eaten by the site from the wasp larva. So this is how we control biologically the pests in the crops. It's important to know to understand what we are doing in our work. Today, the producers that use this kind of biological control need to deploy that kind of cards, which seems like a business card. Inside that business card, there are lots of wasps' eggs, and one man, one human, goes through the crop, deploying manually these cards all over the plantation. So it's lacks an intelligent and effective way to deploy this kind of wasps. It's hard working. It's a hard working task. Walk through the crops, putting this, and a very impressive, very. It's a human task to do. Okay. It's not can be. It's impossible to use airplanes to do this because the airplane need to fly a little bit more high than it's possible to put this kind of effects. I will show you a picture of the drone, which automatically deploys this kind of eggs. And we work in biological control with UAVs. The UAV will deploy the eggs into the crop. It's an ecological and sustainable alternative to pests, but there is a lot of challenges because drones like this consumes lots of energy. We need to planning the route, the path with return to launch. We have different shapes of the areas of the crops. It's not regular. There is a distance between the lines in the crops that the drone must fly over. It's actually the problem is covering path planning, like problem, cover path planning like problem, with multi-flights, because the plantation, the crop is very large for one single flight. So this is the problem that we are facing with our work. We developed a framework where the operator draws a polygon over the area that must be flied. The drone must be flied. Set some parameters like speed, distance among the lines of the crop that the drone must go through, the the altitude of the flight. Also, the takeoff and landing point are defined by the operator. And after that, the framework generates automatically the coverage path planning. It is sent to the drone, and drone executes the mission. So it's a way to, this framework is a way to, with a system, to plan the mission of a drone to deploy the eggs of wasps in a crop. The framework is a system that must be used in the scenario of farms in Brazil, which there is no internet connection, and the computer must be a simple one. It cannot be sophisticated computer. So it's a low-end, very simple, ordinary computer or tablet. The framework was developed using the web technology. It's a browser. We are seeing the image of a browser. I selected to plan flights, a mission. We can see the menus. When you choose the area, you set the parameters over here. And this is the framework generates all the paths automatically. We can see here the most interesting part of our framework, that it's impossible to cover all these areas with one flight. Drone must, it's a mission with two flights. So the framework separates the two flights with the landing and takeoff area, takeoff point. So we load this mission planning to the drone. After the flight, we change battery and run this mission plan. Another interesting that I must highlight is the green land markers over there. These are uploaded to the drone. It triggers the system to open and to deploy the eggs. So the framework computes everything automatically. We run some experiments in the field with a real drone, which is more simple than the company uses for security and economics. We compare how a human operator do it, or how the human operator of the drone usually did it, and how the system, the same human operator using our frame. So we use this drone, and you can see that in average, our framework obviously increases reduces the time of setup because it's everything automatic, and the correctness. There's no way of defining that lines over the field and the distance among that lines and the split of the area in two. This is a very complex task for a human using satellite image. So it's much more precise, and the flight was 4 minutes longer because of this. When we choose better the launching points, the takeoff and the landing, and the system does it automatically. This is the scenario we experimented. It's a very simple one because for humans, when the area is not regular and simple, it's much more harder to define. The area that I showed first is very hard to design the path. More irregular the area, more time to draw the routes. So this is a manual one, and this is the framework designed by the framework. Okay, we are proposing a framework for aerial coverage platform emissions using UAVs for biological control. It's working and it's experimented on the field, in the field. It was tested in real flights. It brings much more agility in the managing the emissions on the field. For the same person, the average error was 18% versus 1% with the automatic, with the framework. And this is the beginning of our work because we need to improve this framework using these two directions. There is two state-of-the-art algorithms for coverage path planning, which is the authors aims to reduce the time of the flight using artificial intelligence techniques. So it's an energy-aware spiral coverage path planning for UAV photogrammetric applications, which is a very similar application, and coverage path planning for UAVs photogrammetry with energy and resolution constraints. The resolution constraints is the altitude of the flight constraints. And we need to investigate different decomposition methods to split the area for each flights, because it's hard to define which decomposition is better to improve the time of the flight. So we intend to do these two improvements of our framework as soon as possible. And that's it. Thank you very much.
Okay, thank you, Paul. I would appreciate if you have any questions for him, please. Hospital.
Two questions. The first one is why I choose draw? Is it because of the draw? So where actually what was the reason to use draws? The second one is what's the criteria to select where the eggs should be?
Can state you're going to be the next one.
Okay, we choose drones because it's we cannot apply airplanes because the altitude of the flight, and because in rovers or terrestrial vehicles, the forest is very hard to navigate to, even for a human. Horse maybe, horse robot could do this test because the crop is it's a messy floor. So drones is a good choice for the what kind of drone? We are using fruit crops, grape, orange, that we have in our city, but it can be applied the corn, any other, because the biological control is almost the same using this kind of fossils. So it can be applied in several cultures in crops. And your second question was?
What's the criteria to decide where?
Oh, it's the idea is to split all over the place. So we open that just over the planets. So the idea is to open as the drone flies, and we calculate about the altitude and the speed, so we can open. The idea is to split all over the place. Did you get it?
Okay, thank you for our question. Any more questions?
Currently, Azure things like we are very used to applying what is
but it's not so. It's hard to measure. So I was interested if you know any way of measuring if the eggs are well deployed, because I project that I work, they have a lot of people measuring productivity. So I imagine that measuring the best is also a big challenge. There any way that you can close the feedback to know if you measure?
The answer is no. But it's hard. It's really hard. We thought about any several ways to measure if it's working, but what happens? The Bird View company, which is with us in this project, is the company that runs these drones, and they developed the equipment, the disposal machine, and they were applying this with a manual path plan. So it is used now. So we changed the way they are doing to our framework, and they start to use our framework. And it was much more technical than scientific choice. Okay, they are using, so it really improves the time of the setup of the mission. So they are using right now in every flight the framework, and they are asking for improvements every time. So my PhD students is almost working for these guys than for me. So it happens.
Hello. Pretty well ready for the presentation. It's sometimes works in robotics are mostly theoretical, so it's always refreshing to see such a hands-on application. One of the things you said for future works is to improve how you want to separate different flights. When it comes to UAV applications, especially agricultural applications, one may have really large views of applications. And we know that flight autonomy is one of the biggest challenges that comes to UAV. So do you intend as well to improve not just how to choose the division of the flights, but you said you can divide in two. But you intend on trying to divide in more, or using more UAVs at the same time so you can make it faster on really large groups.
Thank you for your question. We are working with one flight at each time because the equipment is very expensive and these guys fly once at a time. So they fly one. The idea is to divide the area, calculating the best points for landing and taking off, considering the 3 or 4 or any flights. So
currently your framework already works with more than 2 and even more.
Yeah, yes. But we are dividing in a very deadly way. We need to improve the way we are split. And I think that it's possible to consider multiple flights simultaneously, multiple drones using the same approach. But I don't think it will be put in practice because they do not fly.
It's not cost effective, money effective.
Yes, because they fly the drone lands, they change the battery, upload the new mission plane, and start the flight. So this is the way they are working right now. And to split in 4 with 4 batteries, we go through and we make this flight. Each flight is 20 minutes, 25 minutes. It's a real flight. It's very fast. Okay, I wish to leave you to talking rest of the afternoon, but unfortunately I have to go to the next one. And thank you, Paulo, very much for your talk. Pretty interesting. In the next work will be comparative analysis of innovation-based adaptive common filters applied to AUV navigation by Daniele Silva, Adriano Frutuoso, Luis Souza, Ettore de Barros. I believe Adriano will present it. Yes. Okay, so thank you, Adriano. It's on you now, okay?
Okay.
We are.
Okay. So, good afternoon. My name is Adriano Frutuoso, and this work is a comparative analysis of innovation-based adaptive Kalman filters applied to AUV's navigation. This presentation is divided in 6 parts: introduction, a mathematical model, a Kalman filter, adaptive Kalman filter, results, and conclusion. So, Pirajuba is a torpedo type developed by the team of the Unmanned Vehicles Laboratory, LVNT, of the University of São Paulo. In this figure, we have a photo of the AUV Pirajuba in a sea test. Autonomous vehicles require significant quality on onboard localization and guidance information. However, different factors can affect the navigation performance. In the case of the autonomous underwater vehicle, the factors that can affect the navigation performance is, for example, the attenuation of the global navigation satellite systems, radio frequency signals, and the unstable nature of the underwater environment. That can generate some outliers in the DVL measurements. The use of multiple sensors allows increasing the accuracy of information combining the characteristics of each sensor. The integration can be performed using the Kalman filter. The Kalman filter is the widely used method to perform the combination between the IMU, the inertial sensors, and the auxiliary sensors. However, conventional Kalman filter, the covariance metrics of the process and measure noise are fixed in the conventional Kalman filter, non-adaptive Kalman filter. As alternative, adaptive Kalman filter can be used to update the filter statistics according to the evaluation of the filtering processes. So, in this paper, a comparative analysis between the Kalman filter, the non-adaptive Kalman filter, and the adaptive Kalman filter is performed. So, we consider 2 types of adaptive Kalman filter. A conventional innovation-based adaptive Kalman filter, and a robust innovation-based adaptive Kalman filter. So, in this paper, comparative analysis between the Kalman filter based is performed to evaluate the navigation performance. So, the dynamic model adopted in this paper is given by this equation. This equation describes the attitude error, the velocity error, the attitude error, the velocity error, and the errors of the gyros measurements and accelerometer measurements. So consider the dynamic model given by these equations. The state variables of the system is given by this the state variables are the attitude error, the velocity error, the errors of latitude, longitude, altitude, and the gyros bias and accelerometer bias. So this is the state variables adopted by the state space model of the navigation algorithm. Considering loosely coupled INS DVL PS sensor fusion integration, that this type of integration is commonly used in AUV navigation, the observation model adopted is given by these expressions. So we can see in this expression that the DVL scale factor and the misalignment matrix between the IMU and the DVL sensor. So the DVL scale factor error and the IMU DVL misalignment matrix can be compensated in a previous step, specifically in the step of alignment, the initial alignment, and calibration of the navigation sensors. The common filter. The common filter is a powerful tool used in many applications, such as in national navigation systems. So these equations describes the prediction and update stage of the common filter. These equations are well-known expressions that describes the prediction and update steps of the common filter. The adaptive common filter. Adaptive common filter with innovation-based estimation is a technique that that updates the metrics of the process noise covariance and the measurement noise covariance based on the innovation sequence. So, based on the innovation sequence, the adaptive common filter with innovation-based technique updates the metrics of the process noise covariance and the measurement noise covariance. So the conventional innovation-based adaptive estimation update the metrics key and R using these expressions. So this expression describes the update of the measurement noise covariance and the process noise covariance. So in this case, we use the covariance matrix. We use the covariance matrix to update the metrics R and key, and the covariance matrix. The expression that updates the covariance matrix is given by these equations. So in these equations, we have to define the length of the moving window, represented by the variable n. So the robust innovation-based adaptive estimation is a modification in the conventional innovation-based adaptive common filter. In this case, in this paper, we use a robust innovation-based adaptive common filter based on the chi-square test. The chi-square test examines the frequency of observation of the estimates and identifies outliers in the innovation sequences. So we have in the robust innovation-based adaptive common filter, the chi-square test is used to identify outliers in the innovation sequences. So we use statistical variables, these statistical variables, to detect the outliers in the innovation sequences. So the hypothesis test is performed according to this expression. So in this expression gives an information that has an outlier or no outlier. Outliers have outliers in the innovation sequence or no outliers in the innovation sequence. Results. The navigation results, these only simulation results, were obtained using the AUV simulator developed by the team of the Unmanned Vehicle Laboratory, the LVNT, of the University of São Paulo. So to generate the results, we use the AUV simulator. We developed the AUV simulator. So the navigation simulations results were obtained for a low Moore maneuver. In this figure, we have this figure shows the low Moore maneuver used in the simulation tests. And at a constant cruising speed of 1 meters per second, with this following condition: the UV aligned with the NAD navigation frame, north, east, and down navigation frame, initial coordinates of 23 degrees and 45 degrees, misalignment DVL, IMU DVL misalignment of 1 degree for X and Y, and 5 degrees for Z, and DVI scale factor error of 5%. And the integration type used in the simulation was the INS DVL PS with sensory fusion. using the conventional and adaptive common filter. So the outliers were randomly inserted into the speed, specifically in the DVL measurements. In the DVL measurements, we insert randomly outliers in the DVL measurements. Simulations were considered using a Monte Carlo simulation with 100 repetitions. So I will present some results of these simulations. So consider two scenarios, no outliers and with outliers. So considering no outliers, this table gives the position error on north, east, and down direction. Consider the conventional common filter, no adaptive common filter, and the robust innovation-based adaptive common filter, and the conventional innovation-based adaptive common filter. So consider the scenario was consider the scenario for no outliers into the DVL measurements. The position error was around was approximately equals. Consider these three common filters, the conventional and the adaptive common filters. The position error was approximately the same. So considering the distance travel error, was around 1.4% of the distance covered, the distance travel error in this direction. So considering no outliers, the performance of the navigation, the navigation performance using the conventional common filter and the adaptive common filter was approximately equals. So consider the scenario with outliers in the DVL measurements. We can see the effect of the outliers in the velocity of the vehicle. For example, considering the common filter, the results for common filter with outliers on the DVL, we can see that the trajectory and the velocity was polluted with outliers in the DVL measurements. So, considering the robust innovation-based adaptive common filter, the effect of the outliers into the coordinates in the trajectory and the velocity of the vehicle is attenuated using the chi-square test. So the performance of the robust innovation-based adaptive common filter is better than the conventional common filter and the adaptive innovation-based common filter. So, conclusion, in this paper, simulation test results were present for navigation systems using INS DVLPS sensor fusion. Performing a comparative analysis between the conventional common filter, or as it no adaptive common filter, and innovation-based adaptive sensor fusion with and without robustness. And the conventional common filter had a significant increase in errors with the insertion of outliers in the DVL measurements. The robust innovation-based adaptive common filter showed a high level of robustness to outliers and a better performance compared to the conventional innovation-based adaptive common filter and the conventional adaptive common filter. So in the future, we intend to perform the field tests to conduct it. We intend to perform field tests for evaluate the performance of the robust innovation-based adaptive common filter in a real time. So the authors are grateful to FAPESP for funding the project and to CNPq for funding the student scholarships. So, and that is all, and thanks for the attention.
Okay, thank you, Adrian, for your presentation. Very good. And if you would like to make some questions, please. Otherwise, you'll have to make it again. Looks like when we talk about common filter, people stay a little bit away from it. You're courageous. What? Okay.
We have
And I'll make you fast question, Adrian.
Yes.
So you use the common, you compare the common filter with itself. Did you think you can go, or what is the performance of it with other kind of algorithm? Did you think about that?
Yes, we implement some other strategies of adaptive common filter. For example, we implemented the multiple models adaptive common filter and the residual based adaptive common filter. So the best performance for considering no outliers was obtained using the innovation-based adaptive common filter and the Robbins innovation-based adaptive common filter. For consider the question of the space of the article, the paper, we focus only in the innovation-based adaptive common filter and the convention-based adaptive common filter.
So everyone, the state of the art are common filter based, basically. Common filter based, basically. Okay, thank you very much. We are going to move to our next presenter and close to him. Now, the last presentation of this session, exploring ground effect in a hybrid aerial aquatic unmanned vehicle. It's going to be presented by Pedro Miranda. Okay. Pedro.
I'm in the link. Okay, so hi everyone. My name is Pedro Miranda Pinheiro. I'm with the Hydro team. We are a competition and research project from the Caltech, from Intelligent Robotics and Automation Group, from the Computer Sciences, Center of Computer Sciences of Universidade Federal do Rio Grande. And this work is partially funded by CAPES, CNPq, and the PRH from the National Agency of Oil and Biofuels. So in this work, I'll be talking about the ground effect in a hybrid area aquatic unmanned vehicle. Can you hear me in the back? Okay. So this work was done. Sorry. This work was done by Vivian Roque, Paulo Errold, myself, César Silva, Diana Cardoso, Paulo Cunha, and Paulo Deus. So I'll start with an introduction. So hybrid manned aerial vehicles are these vehicles that can navigate in both air and water. They usually do it autonomously, this transition between air and water. And this field of robotics is right now being studied. Many works from 2010 till now. And mainly the applications are focused mainly the universities and institutes are focusing on military applications, but we understand there is a lot of room for civil applications. So that is it. So the main challenges for this kind of vehicles is that they are high cost and high risk experiments associated with it. So we tend to work a lot on models and simulation, since we have only a few of vehicles working in the world, and many of these vehicles are military, so they do not open their hardware techniques. The communication with these vehicles in the air, it's okay, but underwater it's still an issue because we have weight constraints, which is also a great challenge. And we also have really complex nonlinear dynamics. Once we are changing the medium, so we are going from air into the water or from the water into the air, and we have a abrupt change in dynamics. And this is a really great issue. We are really used to using ROS to solve many of our problems, simulators like Gazebo, but we don't have a hybrid simulator as Gazebo. In Gazebo, no plugins. So we work in a simulation that we developed, work in a model that we also developed. So the contributions of this work, we are trying to improve the mathematical model of these AGUAVs so that we have a more real life like simulation. With this ground effect for hybrid air aquatic vehicles, we understand the ground effect is an issue for many UAVs. So this is also the case. Since we are going to demonstrate the significant impact of the water exit with the ground effect. The classic UAV model. Difference here is that we have a mass term for the vehicle, but we have additional classic equation. Plus the other mass, acceleration, correlative effect, drag force, gravitational, and buoyancy forces on the vehicle. Now the transition zone model, there is many ways you can do it. Thing to do would be using numeric simulation, but we don't have time for that, especially when we are focusing in other algorithms of robotics. A more simpler transition model, which is so we consider we use a sigmoidal function, specific masses actually. Changing the fluid specific facilitates a lot the simulation, and then it allows us. So this is the grounded. It's from the 1950s. It was developed mainly for helicopters, but here we have works demonstrate that it can be used. And what it does, ground effect and the truck out of ground effect. So when it distant, when it is close to the ground and when it is far away from the ground. And even radius and the vehicle altitude. Just out of ground effect is a classic so now what we did, we wanted to understand if there is a great, considering the ground effect, why kind of vehicles. So we ran a first here we if while doing my navigation with the same if there would considering ground effect. So when he approached, so into the water, there is no great change. It's the same. We only have sure. When we consider the second study case, we are immediate then ground effect will be when it comes out of the water. Because we can have some obstacles. Some significant finding. Literature does not consider we understand why. And while works just fine. Or zoomed in, this just spikes, and this is in the ground effect because force first force vector, and this makes the sequence of ground effect in AGU negligible. In Atitude and out perform experiments in with prototype to
Okay, thank you for your presentation. We still have time for a couple of questions, please. No? Oh.
You can't find well-built environments in gazebo for your 5% days. And you are improving mathematically, but you already have. Do you intend to integrate this with gazebo or other column simulators?
yes, yes, because I was also talking with a colleague about this, but Gazebo is a pretty good framework. It integrates a lot of sensors and commercial sensors and actuators. So yes, we intend to integrating with Gazebo, but it's not really clear how we do that, because it's very time consuming, and I don't know yet we have the people to manage this kind of process. But yes, it would be great if we could. I think the community would appreciate a lot, because most of us work on our own simulations. But yes, we want to.
It's easier to have objects and other robots and other sensors.
Mhm.
Because you will never seen anything like any water. So a lot of projects might be connected source.
Mhm.
You will have a lot of community and emerging
Yes.
research. So I think probably.
Yes. Thank you. Yes, Gazebo has in the competition we have worked with water simulation for drones, but we don't go into the water. We land in objects that are on the water surface. But yeah, we already have the scenarios. We just don't use underwater operation for this kind of vehicles. So yes, we intend to produce this kind of plugin and make it available for the community, but it's not yet clear how we do that with the time and resources you have. Thank you.
Okay, thank you very much. Okay. I think we still have time for a short break, coffee break, previous to the next. We have 5 minutes for coffee break.
Olá, pessoal, muito boa tarde, tudo bem? Sejam todos muito bem-vindos aqui à nossa palestra. Agradecemos desde já pela presença. Só vou pedir uma gentileza para a gente fazer a nossa abertura oficial. Vou convidar o pessoal que está aqui no fundo para vir aqui à frente, ficar mais pertinho aqui do nosso palestrante, por gentileza. Tá? Quem puder vir aqui à frente para poder interagir com mais facilidade, ficar mais próximo do palestrante, tá bom? Bom, pessoal, novamente agradeço a presença de cada um nessa tarde movimentada que estamos tendo neste evento, né? E, bom, agora daremos a abertura oficial aqui da nossa palestra com o João Pedro, nosso convidado. Ele que vai falar sobre as competições de robótica, né, e do mercado de trabalho, desenvolvendo hardware no Brasil. Ele que é engenheiro de hardware da Jacutian. Bom, então vamos seguir agora com a palestra. Passo a palavra para o Pedro. É isso. Muito obrigada, pessoal.
Boa tarde, pessoal. Como já foi introduzido, eu sou o João Pedro. Vou passar um pouco algumas coisas aqui de como a gente desenvolve o hardware lá na Traction e, consequentemente, aqui no Brasil, né? Vou passar também um pouco da história do que eu passei aqui na própria CBR, Robocamp, robótica. Eu comecei os eventos de robótica em 2008. Eu tinha 10 anos e fui até 2014. Então, eu passei uns bons anos da minha vida vindo todo ano, correndo atrás do Brasil para esse tipo de evento de robótica em si, né? Passei pela UBR, pela CBR, pela Robocamp daqui, do Mundial e todos esses outros fatores. E hoje eu mexo com a mesma coisa que eu trabalhava antigamente. Eu mexo com desenvolvimento de hardware, desenvolvimento de produtos lá na Tracker. E o que é a Tracker? Eu sou um videozinho rápido aqui, deixa eu ver se ele vai dar play. A gente está um pouco sem som aqui, mas a Tracker é uma empresa brasileira de desenvolvimento de sensores IoT para aplicações industriais. Então, a gente desenvolve sensores que vão acoplados a máquinas das indústrias e a gente faz coletas dessas máquinas, da vibração, da temperatura e de vários aspectos de funcionamento dessa máquina ao longo do tempo. Esses dados são enviados para, basicamente, esse é um sensor, vou passar também. Deixa eu voltar. Esses dados são enviados para os nossos servidores, onde a gente tem um tipo de IA que analisa esses dados com os dados passados e, a partir disso, a gente consegue detectar vários novos tipos de problemas e prever alguns tipos de problemas também que estão acontecendo nas máquinas, né? A Traction é uma das maiores startups no Brasil desse segmento. A gente foi recentemente eleito uma das 100 startups to watch, né? 100 startups para se olhar no Brasil e para ter atenção à existência dela. E recentemente nós tivemos 2 investimentos grandes, totalizando mais de 100 milhões de reais para o crescimento e desenvolvimento dos sensores e de tudo na empresa. Eu passei rapidinho aqui mesmo. Aqui uma vez. Esse vídeo aí vai passar tranquilo. Então, tá ali o sensor medindo a vibração dessa máquina, a temperatura também, e a gente consegue, por meio de um aplicativo, por meio de uma plataforma, avisar o usuário, o manutentor, a pessoa lá da indústria, de que há algum tipo de problema. Além disso, o sensor fornece várias informações de oímetro, quando a máquina está funcionando, quando ela não está, e eles utilizam isso para ver se tem algum tipo de parada não programada. Eles colocam no sistema o funcionamento da máquina, por exemplo, das 8 às 8 da noite. Se ela parar em algum momento dessa parte do dia, a gente consegue identificar pela vibração da máquina e avisar o usuário, avisar a pessoa de manutenção, para que ela consiga deixar o menos tempo possível a indústria parada, porque a indústria parada gera perdas para a fábrica e é isso que a gente foca em resolver. Então, teve também recentemente, né, o nosso novo sensor. E aqui é uma breve introdução também. Eu, desde criança, como eu falei, desde 10 anos de idade, lá em 2007, 2008, eu comecei a participar da UBR. E desde então eu não parei até 2014, quando eu parei de competir na parte
júnior e passei a competir na parte da CBR, competi até 2017, 2018, por aí, no futebol de robôs também. Depois disso, eu dei uma passadinha numa startup que eu tentei começar, e está ainda por aí, que fez o primeiro satélite brasileiro a ser enviado para o espaço pela SpaceX. Então, eu estava um pouco nessa parte de hardware também, dessa startup. Então, eu desenvolvi e trabalhei na parte de engenharia do PAN-BR1, que é um dos primeiros satélites brasileiros por uma startup também. E depois eu passei a ser engenheiro de hardware lá na Traction, que realmente era um lugar que estava precisando e ainda precisa de gente boa, como a gente consegue encontrar aqui na parte de engenharia e na parte de criação de produtos, programação e etc. Então, vou passar um pouco mostrar um pouco só. Já participei de quase todas as modalidades desse evento da robótica, né? Rescue Base, Soccer, Rescue Line, futebol de robôs. E aqui tem só um pouco dos prêmios que a gente tem lá na escola onde eu estudava. Até 2014, 2013, a gente tem prêmios de primeiro lugar, segundo lugar, prêmio da RoboCup Internacional. A gente conseguiu, durante muito tempo, ter uma trajetória bem legal nos eventos de robótica e construir e entender várias coisas desse processo. Tem um vídeo rápido aqui que está bem os robôs funcionando, né? A gente, lá em 2010, 2011, começou a trazer Arduino e a trazer mais eletrônico para os robôs, que a maioria das vezes o pessoal fazia com Lego ou alguma coisa assim. A gente estava ali, esse ano que é 2012, mais ou menos como pioneiros de trazer Arduino e trazer uma eletrônica mais pesada, mas você fazendo do zero as coisas para a modalidade. Isso a gente desde mais ou menos 2009 lá, quando a gente veio com a Arduino para as competições. Aqui tem uma foto minha, um vídeo, na verdade, desmontando o robô, que era um misto ali de Lego com Arduino, né? Ele tinha um sensor que foi hackeado para funcionar com Arduino, mas o sensor era Lego e etc. Então a gente construía tudo de uma forma que ficasse simples, que ficasse fácil de fazer e sem perder a atenção para um design mais legal, para alguma coisa assim. Então a gente sempre pensava no robô e naquilo que a gente estava fazendo, às vezes como se ele fosse um produto mesmo, né? E isso que eu vim fazer depois na Crashing, etc., de desenvolver produtos, desenvolver hardware mesmo aqui. E esse é um pouco dessa parte. E aí, começando o processo da parte de desenvolvimento de hardware, eu vou passar um pouco sobre o processo, como é feito mais ou menos da maneira padrão, e depois eu vou contar como a gente mudou um pouco disso e fez desenvolvimento lá na Traction de uma forma que ficasse um pouquinho melhor para uma empresa que está crescendo e mudando sempre a sua forma de fazer alguma coisa, a sua forma de fazer um novo produto, seu desenvolvimento é mais acelerado e a gente não se encaixa em coisas desse processo mais antigo, vamos dizer assim, de fazer, desenvolver produtos. Né? Então, a gente geralmente se começa ali com design, engenharia, junto com uma galera na sala, faz a ideação do projeto, vem com um tipo de conceito, faz ali o design daquilo tudo, fala, esse vai ser o nosso produto, vamos fazer a engenharia dele, e aí vamos para a parte de prototipagem. E nessa parte vai se produzir um sensor, vai se fazer um teste, vão se adaptar algumas coisas de acordo com o teste ali, e depois vão ter algumas interações por causa das adaptações que precisaram ser feitas. E no final vem ali a produção em larga escala, então você planejou um produto aqui, fez alguns testes, construiu ele, e depois lá no final você fala, bom, agora eu vou produzir ele em larga escala. E basicamente, nessa parte de produzir, você tem que pensar no mercado, nos fornecedores, na parte de lançamento e marketing, que é super importante para um produto que vai para o mercado, e também você tem que pensar em dar suporte e em todo o ciclo de vida desse produto, né? Até quando ele vai ser vendido, até quando você tem que dar suporte para aquele tipo de produto, e geralmente é para a vida inteira, porque ainda vai ter produto na mão de um cliente ou algo assim. E nessa parte do design e engenharia, a gente tem sim essa parte de ideação, né? E nessa parte de ideação a gente define uma necessidade, o que a gente está querendo resolver, e etc. Vem com um conceito ali, define o que vai ser aquele produto, o que aquele produto vai resolver ali. E na parte de design a gente geralmente ia ali de um designer, eu esbocei uma coisa aqui, vamos agora para um protótipo funcional,
E na parte de engenharia a gente desenvolve o produto de uma forma que ele fique confiável, né? Geralmente na parte de design aqui a gente só esboça, desenha algumas coisas, desenha as funcionalidades, mas não produz aquilo ainda assim, né? A gente vem depois para engenharia para fazer aquilo de uma forma que seja confiável e que funcione ali 2, 3, 4, 5 anos durante a vida útil do produto inteiro. E aí, passando para outra parte que a gente falou agora, na parte de prototipação, geralmente na parte de manufatura a gente cria uma versão física do produto, a gente testa o produto, a gente adapta alguma coisa, adiciona, remove funções, e a gente pode iterar sim, mas é algo que a gente faz ainda nesse processo. A gente ainda não está vendendo ele em larga escala, não está fazendo nada desse estilo. E mais para frente a gente vai ver que na Track a gente estava mais ou menos no processo de adaptar e iterar, e já tinha uma venda de 4, 5 mil sensores, e a gente tinha que pular muitas etapas dessa, e a gente teve que desenvolver um pouco de um método diferente para que isso acontecesse e fazer isso de uma maneira que fosse interessante tanto para a gente quanto para os clientes, para que a gente não ficasse enviando produtos que ainda não foram testados e que ainda não têm funcionamento certo. E o funcionamento confiável. Então, nessa parte do processo, a gente geralmente tem a parte final, né, de produção e a parte de escalar esse produto. A gente tem também o ciclo do produto ali, que geralmente é a introdução dele no mercado, o crescimento, o produto está maduro, ele fica por um tempo ali, mas geralmente tem-se um declínio no final da vida útil do produto, onde a gente já está pensando na próxima versão do produto, né? Ele subiu durante um tempo, a gente vendeu bastante aquele produto, depois a gente está no declínio do produto e a gente tem que já ter proposto talvez um novo produto, algo assim, a gente se planejar também para o quanto tempo, né, é o ciclo de vida desse produto. E já adiantando também, a gente não tinha tanto tempo assim para fazer, porque a gente foi entendendo como a empresa foi crescendo junto dos clientes, a gente foi entendendo que o cliente precisava de alguma coisa diferente do que a gente estava propondo ali. Então, a gente não tinha um produto que a gente falava, olha, esse produto aqui vai acabar daqui a 3 meses. A gente tinha um produto que a gente ainda estava crescendo junto com ele, fazendo e mudando. Então, a gente não tinha uma data fixa para o declínio, né? Não tinha uma data fixa para ele acabar ainda. E é sempre importante também fazer essa parte, né, de um produto, da parte de lançamento, marketing, etc. Então, muitas empresas produzem aquilo, guardam ali 1.000, 2, 3 mil unidades no estoque e aí vão fazer um lançamento. A gente também teve que fazer muita coisa no meio do caminho, assim, né? Tá aqui, vamos lançar o produto agora, porque já tem produto, cliente pedindo função nova que a gente já tem, mas teoricamente a gente não lançou isso ainda, então vamos ter que lançar, porque assim a gente consegue mais vendas e consegue mais coisas para a gente atingir ali, mais problemas a gente conseguir resolver, consequentemente mais clientes e mais coisas para venda para a empresa. Então a gente percebeu que tinha algo de errado nesse processo, né? Esse processo, como eu já falei, ele cresce um pouco devagar, né? À medida que você está ali, se você para, por exemplo, uma equipe lá de desenvolvimento para em uma empresa que é uma startup, uma empresa que geralmente é menor do que as outras, tem uma equipe mais enxuta e etc. Se você para essa empresa para desenvolver, né, só um produto ali, ele vai ficar parado só naquilo e os outros produtos, ou o produto atual que você está mantendo, ele não vai ter atualizações, correções de bugs e nada assim. Então, você não consegue crescer de uma maneira mais rápida como a gente estava crescendo, né? A gente é uma empresa de 3 anos e cresceu, pelo menos no último ano, mais de 200, 300% que a gente era no início dele. Então, isso também não se adapta a essa volatilidade do mercado, né? Vamos supor que você faz um produto que está ali e pega temperaturas de 10 a 100 graus. E aí o mercado agora começou a usar máquinas que têm uma parte mais fria ali, de menos 10, menos 5 graus. Se você planejou seu produto inteiro antes para uma temperatura maior, agora você tem que se adaptar e mover isso no meio do caminho ali do seu teste, justamente cuidar dessa parte da volatilidade do mercado, né? Tanto essa parte que eu falei de o mercado pode mudar, mas também pode chegar ali do seu lado um concorrente seu que fala, não, eu consigo temperaturas abaixo de 0 sem problemas.
E aí você tem que se adaptar para que você não perca mercado para esse novo concorrente que faz algo que o seu sensor ali não faz. Então, se você fosse esperar o declínio desse produto para só depois introduzir uma nova versão que traz essa funcionalidade, seu concorrente ia passar suas vendas, porque tem mais gente que precisa daquela funcionalidade também, né? Então, você tem que estar sempre atento a essa parte da volatilidade do mercado. Tem muito desse ciclo de desenvolvimento de produto que é focado no projeto, né? A pessoa está ali, vamos montar um sensor X. A pessoa foca no projeto, que nossa, vai ter um sensor e etc., que faz X, Y, Z, mas não foca em duas partes que são essenciais para a gente na prática, que são o consumidor e a parte do produto. A gente montou uma coisa que é bem focada no que o consumidor está precisando, mas sem ter aquilo de fazer tudo que o consumidor pede na hora que ele fala, não, preciso A, B e C, senão a gente ia ter de novo uma sobrecarga da equipe que está desenvolvendo, só para desenvolver para um consumidor ou outro. A gente teria algumas limitações assim também. Né? Mas esse processo também dá uma importância maior a parte metodológica daquilo. Né? Se testou por A, B, C e D, que é isso que é o teste que a gente tem que fazer, passou nesse teste, vamos para o mercado. Mas, às vezes, tem alguém na sua equipe, por exemplo, que teve uma experiência de outra área, tem gente na prática de todas as áreas, automotiva, da parte de sensores também, da parte de desenvolvimento de hardware mais avançado, assim, de FPGA e etc. Então, tem gente que tem vivências diferentes que pode trazer algum insight diferente ali do que você está fazendo, né? E se o processo for mais engessado e só for focado na metodologia X, a gente não consegue ter essa flexibilidade também para atender um novo tipo de teste, um novo insight que essa pessoa possa trazer mesmo. E aí a nossa solução, como eu já falei, a gente tem como um dos valores a obsessão pelo consumidor mesmo, né? Então, o consumidor está trazendo para a gente ali de muita importância, mas, como eu falei, a gente faz meio com a média ali que os consumidores pedem. Né? Se todo mundo começar a pedir, por exemplo, nossa, mas eu queria que o sensor fizesse, por exemplo, um alcance de 800 metros, 1 quilômetro do raio da comunicação do sensor, e etc. Se todos os clientes estiverem pedindo isso, a gente com certeza vai focar nisso, porque a gente sabe que isso é uma dor do cliente. E quando o cliente vê algo que foi resolvido para ele ali, né, algo que foi solucionado o problema dele, ele vê muito mais valor naquela solução. E aí a gente falou isso também, que as pessoas, né, são o segredo e a alma do projeto, então a gente bota as pessoas no centro do desenvolvimento mesmo, então todo mundo tem tempo ali, espaço para dar sua opinião e construir o projeto junto com todo mundo. E a gente trabalha num sistema que pode ser visto até como meio caótico, mas é esse sistema que traz e gera diferentes ideias e diferentes problemas que a gente tem que resolver, desafios que a gente tem que atacar mesmo durante o dia. E a gente tem também, durante essa parte de desenvolvimento de produto, né, o modo de se mover rápido e consertar coisas. Então, a gente está desenvolvendo uma nova versão, uma nova funcionalidade para o sensor, a gente já está querendo conversar com o cliente e falar, opa, você pode ajudar a gente no teste desse sensor aqui? Coloca lá e fica monitorando, e se isso der problema, a gente já pode consertar isso um pouco antes do teste, mas o nosso cliente ele já vai ter um sensor a mais ali na empresa dele, já vai ter uma coisa diferente que ele pode ir testando, e se der errado, a gente conserta coisas e vai seguindo. Né? Então, a gente traz essa hora de ir para o mercado para um pouco mais para frente, e se der problema, a gente assume o problema e fala, não, a gente vai fazer a troca, a substituição ou alguma coisa assim, mas o cliente está ali sabendo também, né, que essa unidade, por exemplo, é uma unidade de testes, etc. Então, tem esse acordo assim também. E aí a gente fala que a engenharia sobre o mundo real, sobre problemas reais, justamente que a gente faz os sensores, a gente faz essa engenharia para resolver problemas reais que as pessoas têm lá. Né? Então, o pessoal da manutenção, no caso da Tracking, tinha muito problema de máquina parando, e esses problemas são problemas que custam bastante para toda a indústria e que podem, às vezes, a máquina, às vezes, ela não escolhe quando vai parar. Às vezes, ela pode parar no sábado, no domingo, algo assim, e ela para de funcionar completamente. Porque, segundo o módulo manual ali de se fazer esse tipo de análise que a gente faz, o pessoal vai até uma máquina 15 dias, ou de cada 15 dias, ou de cada mês,
ou de cada semana, toma uma medição do aparelho e volta. E depois de 15 dias, toma outra medição de vibração do aparelho e analisa e fala, não, tá tudo ok. Mas nesse período, a máquina pode quebrar. E, geralmente, ela quebra no pior dia possível, né? Ela quebra na sexta-feira, às 6 horas da noite, onde você não tem... você tem que sair ali ou ficar na empresa e isso aumenta bastante, né? E o que a gente costuma dizer é que a gente resolve esse problema justamente pegando a falha ali no início do processo, né? Então, a gente já vê ali, pela vibração mesmo, que tem uma falha no rolamento, uma falha em algum tipo de peça assim, e já avisa um pouquinho antes. E nesse caso, é o manutentor, né, a pessoa com um problema real ali, que escolhe quanto ele vai parar para dar uma análise na máquina. Então, ele não para porque a máquina quebrou e ele tem que ir lá e são 7 horas da noite e ele já estava no caminho de casa e tem que voltar. Ele fala, nossa, amanhã que é sábado, a gente faz um turno a mais aqui e para essa máquina, dá uma olhada no problema e vê como é que ela está. Então, a gente evita problemas antes que eles aconteçam, né? Isso é um problema real lá da parte da indústria. E aí, na prática, nada é muito feito fora dessa nossa cultura, né? Tem alguns princípios que a gente tem da cultura da Tracking, que é a cultura, a primeira parte da cultura do CAP, né? E todo mundo sempre se encorajando a ser protagonista daquilo que está fazendo ali mesmo, né? Então, mesmo se alguém às vezes fala, pô, não sei se eu vou conseguir matar essa tarefa aqui, a gente fala, cara, vamos pegar, vai dar certo, a gente está aqui para do lado auxiliar se der algum problema, a gente vai resolver isso junto ali, mas a gente está sempre encorajando uma outra a pegar aquilo e matar ali e ser protagonista no produto ali, né? Então, todo mundo tem essa ideia de que o produto é feito por quem está ali na parte de hardware, desenvolvido pelas pessoas que estão ali, né? A gente tem também como uma parte da nossa cultura a parte de transparência mesmo, né? Então, se você vai dizer alguma coisa sobre um colega de equipe seu ou algo assim, a gente prefere que seja dito para a pessoa mesmo, que você fale, né? Essa pessoa não pode ter essa preferência demais ou algo assim, então tem um certo nível sim, mas a gente, nesse caso, tem toda a liberdade de falar, cara, tá meio ruim essa solução aqui, vamos trabalhar para fazer alguma coisa diferente nesse processo, vamos mudar essa solução, vamos fazer uma coisa diferente aqui, e não deixar que, nossa, tá uma pessoa fez um código muito ruim ali, então desenvolveu um hardware horrível e tal. A gente está sempre lá dentro buscando ser transparente para que dentro da própria empresa não haja um tipo de briga ou divergência que prejudique o produto e no final prejudique a solução do problema ali do nosso cliente. E tem também um dos valores, que é a parte de brilho, né? Que eu acho que é um dos mais importantes também, que é entender que realmente uma tarefa complexa que você pega ali para fazer é o resultado da divisão dessa tarefa em tarefas muito menores que você vai fazendo ali ao longo do caminho, né? Então, todo mundo lá procura, quando chega um problema maior ou algo assim, procura ajudar quem está matando aquele problema ali a dividir ele em problemas menores para que a gente consiga matar ali aquele problema mesmo. E aí, o da Tracker, né? A gente tem um processo que não é meio que linear, igual que eu estava mostrando aqui agora, né? É um processo que a gente consegue ver que as setinhas elas vão e voltam, e sobem e descem, e etc. Então, a gente primeiro vai no consumidor, procurar as dores e nas pessoas que vão consumir o nosso produto, e a gente encontra esses problemas que eles têm aqui no mundo real, né? E a gente procura entender esse consumidor, procura entender o que ele tem para dizer para a gente, e com isso a gente encontra, né? A gente tem engenheiros ali reais que resolvem problemas reais, como já disse antes, e a gente define muita coisa que na verdade, os não objetivos. Que é aquela parte de a gente não vai atender tal coisa e ponto final, sabe? Se a gente ficar abrindo muito o escopo de um projeto ou algo assim para uma coisa só, a gente, no final, sai muito do caminho que estava dito ali, né? Então, a gente tem um sensor de vibração e temperatura, por exemplo. Então, a gente não desvia muito de, pô, o cliente pediu para a gente analisar uma outra coisa nesse sensor, já está do lado da máquina dele que faz uma parte ali que precisa de uma análise de CO2 ou algo assim. Só que a gente fala, cara, se a gente for fazer isso, é um novo produto, não é parte desse produto, né? O produto, ele tem os outros não objetivos, né, bem definidos. Ele tem ali, olha, isso aqui a gente não vai atacar com esse tipo de produto, a gente vai definir um outro tipo ali. E, em paralelo a essa parte de pesquisador do consumidor, a gente faz a parte de prototipação, então a gente já vai pegando fornecedores, já vai desenvolvendo, já vai dando suporte também. Então, a gente viu uma dor, a gente já chegou a fazer um sensor inteiro de uma nova modalidade em menos de um mês para entregar em outro cliente. E hoje ele é um dos novos produtos da Traction também, que a gente está vindo agora com um sensor de medição de energia e etc., também para máquinas. Então, a gente trabalha analisando máquinas que são rotativas, com a parte de vibração, e as que não são rotativas, a gente consegue analisar agora com o sensor de energia. Então, essa parte surgiu lá de uma petição ali, um problema de um cliente que a gente foi resolver justamente com, não no produto que a gente já tinha, mas com um produto novo. E esse produto novo precisou ser desenvolvido e já testado no cliente. A gente fez um em 15 dias ali e colocou no cliente. Deu problema, a gente teve que voltar lá, pegar e resolver mais uma vez essa mudança. E a gente vai integrando tudo isso e quebrando as coisas, mas consertando elas rapidamente depois, para chegar a um produto forte. E depois a gente vai fazer, claro, a parte de marketing e a parte de escala. Então, a gente primeiro produz aquele produto em poucas unidades, ali 100, 200, e vai testando com os clientes mais próximos, testando lá no próprio parte de desenvolvimento, né, no departamento de pesquisa, e depois a gente passa a essa parte de marketing escala e a parte de documentação, entender, e o ciclo de vida do produto muda bastante, porque a gente não espera ter um declínio, né? No meio da maturidade do produto, a gente ainda está modificando coisas e criando coisas novas ali. E aqui passando por parte em inglês, que não deu tempo de traduzir tudo até agora, mas nessa parte de consumidores e das dores, né, que a gente procura ver, tem até uma imagenzinha ali que a gente vai até a pessoa da manutenção ali, né, daí que vem o Blue Cap, né, a pessoa do chapeuzinho azul ali, e a gente conversa com eles e define esses problemas no mundo real que a gente quer resolver, né? A gente vai entender o consumidor e é muito importante definir ali a persona, né? Quem você vai tratar e quem você conversa ali na empresa, quem é a pessoa que vai te ajudar a realmente entender os problemas, sabe? Porque o problema, por exemplo, para o cara da manutenção que vai lá na máquina apertar o parafuso é mas o problema do chefe dele, que está lá na salinha, no ar-condicionado, é um problema totalmente diferente, né? Então, a gente tem que entender também esse processo de conversar quem é a persona, quem é que a gente vai atacar ali dentro de resolver o problema que ele tem, né? Então, a gente escolhe bastante essa parte também e conversa bastante com a persona para que ela nos diga quais são as dores para a gente poder resolver. E, nesse caso, tem a parte de achar engenheiros de problemas reais ali também, né? E criar um time que está focado sempre em resolver esse tipo de problema de alguma forma. E também a gente define, como eu falei, os objetivos. Os não objetivos e os objetivos, é claro, do processo. Na parte de engenharia de prototipação, né, a gente está sempre definindo ali os componentes e também os fornecedores. Com o mercado hoje de semicondutores, por exemplo, do jeito que está muito difícil encontrar componentes, né, muito complicado encontrar um tipo de componente, ou se você encontra 2 meses depois já acabou tudo que tinha daquilo e vai tudo acabando e diminuindo a quantidade ao longo do tempo, a gente está sempre analisando também e fazendo mudanças no produto para ele receber ali um novo regulador de extensão, um novo processador, se for necessário. A gente está ali para trocar isso e continuar resolvendo os problemas que a gente precisa resolver dos clientes. A gente também está sempre desenvolvendo, né, e testando tanto para o consumidor, como eu falei, ou para o próprio laboratório da Tranca. A parte de suporte também, né, que a gente avalia se o produto resolveu mesmo aquele problema e se o cliente tem mais alguma coisa que a gente possa ajudar ele. Então, isso sempre focado no que o cliente traz para a gente. E também tem essa parte de adaptar o produto e gerar, como eu falei, tá acabando no mercado uma peça X do produto, vamos mudar, vamos melhorar, ou então de problemas do nosso processo mesmo, né? O sensor tinha uma fixação há um tempo atrás com urinas, a gente percebeu, cara, tem uma indústria que a gente estava vendo aqui, que está com o nosso sistema, que tem motores que vibram a 12G, por exemplo. Então, é uma coisa bem, bem forte. E um sensor que está preso com imã ali não segura. Então, a gente teve que desenvolver adaptações e coisas diferentes, inicialmente para aquele consumidor, para aquele para aquilo ali que a gente estava tentando resolver, e depois aquilo ficou ok, a gente conseguiu passar isso para o resto da linha de produção e trazer essa mesma evolução que a gente trouxe para um cliente só, para todo mundo. A gente viu que isso seria bom para todo mundo, seria uma facilidade que teria para todo tipo de cliente, e a gente traz justamente essa ideia. Aqui na parte do produto, então, como eu falei, ele nunca tem um declínio. Ele atinge a parte de maturidade e ele vai sempre sendo estendido com novas funcionalidades, novas mudanças que a gente vai agregando da dor de algum outro cliente ou de clientes novos que vão entrando ali, trazendo novas ideias para o que a gente está fazendo hoje. E a parte de refinar o design também acontece, né, na parte de crescimento e na parte de maturidade, mas ele acontece no meio desse processo inteiro. E a gente sempre adaptando ali para algum nicho específico, algum outro, e depois trazendo esse tipo de dado, esse tipo de solução para outros nichos de mercado. Então, não tem mais o declínio ali, tem agora a extensão do processo. Né? Tem uma parte que é muito particular do Brasil, né? A gente tem sim uma competição grande com produtos, por exemplo, que vem da China, produto que já faz aquilo que sua empresa está fazendo ali e já está pronto, e vem da China a $2, $3, $4, baratíssimo. Tem hoje, né, a falta de componentes, que não só no Brasil, mas no mundo inteiro, só que aqui é um pouquinho mais difícil, que a gente não produz, não tem nada desse estilo, né, da parte de semicondutores em larga escala, assim, então a gente não consegue também ter um acesso legal a componentes. Né? Tudo tem que vir ou da China, ou dos Estados Unidos, e a gente, nesses casos, briga com o mundo inteiro para esse tipo de componente que a gente tenta adquirir. Né? E a parte de impostos e a parte legislativa mesmo é também um certo peso aqui, né? A gente compra o componente, mas quando chega tem que novamente pagar impostos e mais impostos de importação, e no final as coisas valem basicamente o dobro, né, do que a gente pagou no início. Também é um pouco difícil achar a parte de trabalho qualificado aqui no Brasil, né? A gente, inclusive, está com vagas abertas na Triton, se você desenvolver a parte de hardware e eletrônica e a parte de software também, firmware, a gente tem vagas, a parte de data science também tem vagas de várias coisas na Triton, mais de 50 vagas abertas, né? E a gente tem dificuldade, sim, de achar uma galera boa para continuar desenvolvendo produtos também. E também tem a parte de cultura e de incentivos ali a desenvolver aquilo tanto pelo governo quanto mas pela sociedade, assim, né? Quem começa a desenvolver um tipo de produto novo, uma solução nova, geralmente não encontra uma parte, um tapinha nas costas, falando, pô, você vai conseguir, cara. Geralmente encontra mais críticas do que a parte de, cara, você vai conseguir, continua aí, vamos fazer, dar certo, né? Então tem esses problemas que trazem no Brasil, né? Mas a gente costuma dizer que a gente resolve isso com pessoas, então a gente tem um time até meio novo, né, na parte de engenharia, mas um time que todo dia está ali resolvendo esse tipo de problema, desenvolvendo sensores. Já são mais de 8, 9 mil sensores na rua, né, da Traction, em mais de 300 empresas que a gente está hoje. Então, desde empresas automotivas, de Volkswagen, a Hyundai, empresas do ramo de fertilizantes, por exemplo, e todas essas trazem um desafio muito grande para que a gente consiga mudar as coisas. A gente tem um time da parte de engenharia bem legal e consegue usar essa galera para desenvolver. Né? E aí eu trouxe algumas das coisas que eu já trabalhei desenvolvendo aqui, né? Mas que eu digo sempre, que não importa se é um robô para competição ou uma impressora 3D que você vai fazer, que você vai usar ali, eu sempre costumo pensar no hardware como se ele fosse um produto mesmo, né? Se ele fosse, se eu fosse montar uma impressora 3D ou algo assim, eu trabalho com aquilo como se eu fosse vender ali unidades daquilo. Então tudo tem que ser bem feito e tudo tem que ser ali bonito, vamos dizer assim. A gente tem ali essa parte de desenvolvimento, né? Eu trouxe aqui até uma foto de desenvolvimento de hardware que a gente acabou fazendo para uma empresa lá de Luxemburgo, não foi na época que eu estava na Traction aqui ainda, né? Mas a gente desenvolve a parte interna, você pode ver que é meio feia, é armengada, mas a parte externa ali é um negócio bonito, fechado e construído para que seja como se fosse um produto mesmo final para a parte do consumidor, né? E a gente tem que entender também que a prototipagem nunca para, né? E o produto sempre vai ter as versões e versões e versões. E no caso da track, a gente só itera mais rápido sobre essas versões. A gente também tem bastante para a parte de produção, né? Muita coisa de problema na indústria só aparece quando você começa a produzir em escala, né? E a gente tem essa pergunta sempre de como ter esse tipo de processo, esse tipo de avaliação, quando a gente está produzindo algo em escala ali, né? Quando a gente está produzindo 10 unidades, 15 ali para o nosso teste, geralmente não aparece nenhum problema e está tudo beleza. A partir do momento que ele começa a fazer 500 por semana, 1000 por semana, você tem ali um problema que aparece no processo produtivo mesmo. A gente criou, então, cria lá na Track, então, vários dispositivos. A gente tem, por exemplo, aqui uma giga de testes ali, que a gente consegue inserir um painel inteiro, né? Um painel de produção dos nossos sensores. E esse dispositivo, quando a gente puxa a alavanca ali, ele faz o teste interno de todos os sensores, um por um, e já gera, na parte de produção mesmo, um relatório sobre como eles funcionam e se todas as unidades passaram ali no teste. Isso aqui é usado muitas vezes em todo tipo de indústria, e a gente usa justamente para poder detectar esses problemas em escala mesmo, né? Detectar problemas que só acontecem quando você produz ali 100, 200, 300 de uma vez. Alguma coisinha ali vai dar de errado mesmo. Então, a gente também tem testa bastante a integração do produto com outras coisas, né? Então, a gente, por exemplo, tem um painel que fica ali o tempo inteiro plugado na tomada com fontes, por exemplo, só para ser testado o firmware, por exemplo. O software ele é testado ali todo dia, tem sensores que rodam lá com uma nova versão que vai sair para o consumidor daqui a um mês ou uma semana ou algo assim, que está sendo testado naquele momento. E a integração do produto também. Você vê que nessa imagem aqui da esquerda, a gente estava montando a nova versão do sensor, fez uma versão que era transparente ali para a gente verificar toda a interação dentro do sensor ali, se a bateria estava encaixando bem, se a placa estava ficando ok ali dentro. Então a gente consegue sim, ter todo esse desenvolvimento, né? E a gente tem esse cuidado também para estar tudo funcionando, todos os processos funcionando ali à medida que a gente vai desenvolvendo a parte hardware novos, assim. Então essas placas que testando na direita, por exemplo, são testes de um novo fornecedor. E a gente faz geralmente 100, 200 painéis e 200 sensores para fazer esse tipo de teste, para validar alguma coisa, né? Então, a gente aprendeu que com escala você tem sim que fazer uma escala mínima ali do seu produto para que você tenha um erro ali acontecendo que realmente um erro de 5%, se você faz 20 unidades, às vezes não acontece, mas se você faz 200, ele vai aparecer mais vezes, então a gente tem que sim, testar bastante essa integração de todo o produto, né? Tanto o firmware com o hardware, quanto o hardware em si dentro ali, né? A mecânica e a parte eletrônica, se elas interagem ok ali dentro. O firmware, uma das coisas que a gente sabe e descobriu, né? O firmware realmente não precisa estar 100% pronto antes do lançamento do produto, né? Hoje em dia tem uma maravilha chamada over the air, né? Updates over the air, que a gente consegue trocar o firmware dos sensores, por exemplo, que estão nas indústrias agora. Então, a gente tem mais de 9.000 sensores nas indústrias que a gente pode atualizar a programação deles ali só de baixar uma nova versão. Então, a gente tem uma plataforma onde a gente consegue trazer mudanças. E mudanças de firmware podem vir muito bem ali podem vir muito bem depois, né, do lançamento do produto. Nesse caso, a gente antes fazia coletas ali com 8 kHz, né? Mas agora a gente passou para 32 kHz só com uma atualização de firmware que mudou como é feito o controle do nosso acelerômetro e do sensor que a gente utiliza para a medição de vibração lá das máquinas. E aí, as funcionalidades via software, uma update de OBD pode mudar completamente o funcionamento do seu sensor e trazer novas partes, novas funcionalidades. Então, hoje em dia a gente diz que nesse desenvolvimento de produto, uma das coisas que a gente faz primeiro é a atualização remota. Depois a gente faz o resto do código, né? A gente pode, sim, enviar para o cliente com um código base e, no futuro, depois de 2, 3 meses, adicionar uma nova funcionalidade e mudar tudo o que o sensor está fazendo, né? Então, é bem legal ter esse tipo de função antes do início da produção inteira, para que você consiga realmente mudar e você tem até um tempinho a mais ali, né? Suponha que demora 10, 15 dias para chegar no cliente, você tem 10, 15 dias, e quando chega lá, você pode atualizar o código mudar alguma coisa que você encontrou, algum problema que só veio aqui na parte final do desenvolvimento. E aí eu deixo um conselho para quem quiser seguir desenvolvendo rápido, que é o método KISS, né, que é o Keep It Simple, Stupid, que é um método que acho que tem que ser mais seguido, assim, né? Ou eu traduzi como não complica seu burro, porque às vezes a gente tem esse tipo de frase, né, assim, tá meio burro isso daqui, né? Então vamos mudar, vamos fazer um desenvolvimento melhor. Só que a gente tem que fazer isso não complicando, né? Você não pode, como eu falei no início, passar 3 horas ali, passar vários dias tentando chegar numa parte, numa solução para um problema, sendo que ele poderia ser solucionado de uma forma muito mais fácil. E como a gente faz isso na Attraction, é justamente trazendo todo mundo ali para aquele problema, tendo uma comunicação legal ali entre todo mundo, para que a gente consiga resolver bem esse problema de uma forma que não seja complicada, sabe? Às vezes, se a pessoa fica sozinha ali, focada naquilo, ela chega numa solução muito avançada que não é geralmente necessária, né? Ela poderia ter resolvido ali com, sei lá, uma cola quente e no final isso poderia ser a solução do problema, sim, né? A gente já cansado de ver produtos por aí que tem uma bolinha ali, ou então um desvio que foi adicionado depois aí na produção, e isso poderia ser feito sim, então a gente muitas vezes não precisa complicar em fazer várias coisas, várias coisas diferentes ali no produto, a gente só precisa simplificar e trazer todo mundo para esse tipo de solução. E aí eu acabo, tem o seu Let's Be Pushing, que ele sempre lá está sempre pegando todo mundo e falando, cara, vamos resolver o problema, vamos juntar, vamos desenvolver algo melhor aí e vamos justamente trazer os produtos, trazer a parte que a gente está resolvendo para o consumidor para uma solução melhor, cada vez melhor, e que a gente consiga iterar aí e trazer mais uma solução que resolva mesmo o problema que a gente está propondo e o problema do nosso consumidor final ali. E acho que dá para perguntar se tiver alguma dúvida, alguma coisa assim. Mas foi isso. Obrigado. Pergunta para o João Pedro. Cara, esses dias a gente estava andando na rua e basicamente todo mundo que a gente olhava era meio que cliente da Attraction hoje, né? Uma das coisas que a gente não vê hoje em dia é indústrias de base, por exemplo, que a gente não consegue pegar hoje, né? Mas a gente está, assim, na Volkswagen, em São Bernardo, na parte da Hyundai, a Yara Fertilizantes, que é gigante no Brasil inteiro, né? Tem também algumas usinas, a Impasa, que é uma usina muito grande que está por aqui. A gente está também começando agora em alguns lugares da Petrobras, Technip. A Embraer tem todas as plantas monitoradas por sensores da Traction, então, desde a planta de Botucatu, Faria Lima, a parte da Eleb lá, todas as de São José dos Campos também tem. Então, um dos nossos maiores clientes é a Embraer, né, que tem realmente todas as plantas, vários sensores, acho que já passou de 100 sensores em cada uma das plantas da Embraer mesmo, e são mais de 200 clientes em todo o Brasil, mais de 200 indústrias mesmo, né? Tem indústria que a gente não sabe que produz, né, mas ela está ali produzindo coisas, né? Tem a Dexco que produz algumas substâncias e produtos da parte de casa. Tem Gelita, que é um produtor grande de gelatina industrial, que é usada em remédios. Então, são coisas que na indústria a gente geralmente não vê a fundo, mas a gente usa os produtos, né? Então, a gente esses dias foi realmente numa fábrica ali que era gelatina industrial e eu, cara, mas sai daqui, o que faz com a gelatina industrial? A gelatina que vai para casa das pessoas e, na verdade, ela era usada para produzir remédios depois, né? Então, a capinha ali de um remédio de gripe é feita com gelatina industrial que é produzida num lugar que agora tem um sensor lá da Traction monitorando, né? Então, tem muitas empresas, Amstead, Klabin de papel, então muitas empresas de papel e celulose também utilizam. Então, tem muita gente que vê a solução, se apaixona e vira cliente. E assim como, por exemplo, na Embraer, né, o gerente de manutenção das unidades da Embraer viu sobre a Traction, a gente estava em vários lugares na mídia, assim, ele conheceu um pouco sobre a Traction e gostou bastante, começou a fazer propaganda dentro da própria Embraer, e agora a gente está em todas as unidades brasileiras aqui da Embraer. A gente só não tem uma que não é produtiva, que a gente não está, mas a gente está chegando lá também e evoluindo bastante.
Mas eu vou perguntar. Legalmente, se fosse a universidade.
Uhum.
Oi. É mais uma curiosidade mesmo. Vocês têm mais facilidade assim, de conseguir acessar a indústria quando ela é completamente usada? Ou, por exemplo, quando metade da manufatura dela é automatizada, a outra é manual? Sim, vocês conseguem enxergar, vocês conseguem entrar mais fácil quando é tudo automatizado?
Na verdade, é um pouco mais difícil quando é tudo automatizado assim, porque isso geralmente significa uma parada em que você tem que parar uma linha inteira, por exemplo. Então, você tem que ser bem combinado, vamos dizer assim, tem que ser um dia em que o cliente já ia avisar aquela parada ali para que a gente possa, talvez, acessar e instalar um sensor ou algo assim, porque geralmente quando é automatizado, um processo está muito mais ligado no outro, né? Então você começa ali em uma máquina que, sei lá, corta a madeira e a outra vai furar a madeira e fazer alguma coisa assim. E se você quer acessar que fura, você tem que parar que corta, porque tem ali algum tipo de ligação entre elas que você tem que parar primeira. E isso é uma das coisas que a gente ataca bastante também, né? Se a gente monitora, por exemplo, qualquer uma dessas máquinas dessa linha, é uma máquina que a gente chama de uma máquina que é importante ali para aquilo, né? Então, é importante para todo aquele processo produtivo. Então, ela tem vamos dizer que ela tem um nível ali maior do que outras máquinas, ela é mais importante de ser monitorada, porque se ela para, todo o processo produtivo ali também para, né? Então, geralmente quando é automatizado, assim, a gente tem realmente que uma dificuldade um pouquinho maior ali para justamente fazer esse tipo de modificação, né? No YouTube da Traction tem vários nossos clientes e casos de sucesso também, se vocês quiserem conhecer um pouquinho mais. Tem várias pessoas da indústria mesmo contando o que foi utilizar a solução da Traction no seu sistema. Obrigado. Uhum.
Eu estou enxergando a questão do motor. Para determinados anos, eu quero que eu tive, as coisas acontecem praticamente quase parecidas. Né? Então, você trabalha com monitoramento, e eu utilizar falar sobre a interação sobre IoT e inteligência artificial, que você tem aí dentro do seu trabalho aí, no desenvolvimento.
Tranquilo. A empresa, os dois fundadores da empresa, né, são engenheiros pela USP, né? Então, a galera lá, o pessoal tem esse cuidado justamente de fazer o que você está falando, né? Que os engenheiros aqui, por exemplo, são contratados como engenheiros mesmo, né? Ali a gente tinha engenheiros elétricos, engenheiros de controle e automação, engenheiros de várias áreas que são realmente engenheiros de desenvolvimento do produto lá na empresa, né? Então, os fundadores tiveram esse cuidado ali de ter, sim, todo mundo que está trabalhando como engenheiro dessa parte de desenvolvimento de produto como engenheiro mesmo, e na parte de aplicação também, né? Então, se tem um engenheiro que está na parte de vendas, ele também é um engenheiro de aplicações ali, e ele trabalha como engenheiro de vendas e de acessar os lugares e conseguir conectar com clientes, etc. Né? Todo mundo da equipe de vendas e da equipe da equipe de vendas, mais um pouco da equipe de suporte, é engenheiro também, né? Então, a gente procura encontrar engenheiros para esse tipo de vaga, justamente porque, suponho que se a gente está trabalhando com o nosso sensor de energia, por exemplo, ele tem que conhecer o que é um fator de potência, o que é cada uma das nuances da parte de elétrica, para que ele consiga realizar ali a venda e entender melhor a dor do cliente que está propondo ali, se a nossa solução se encaixa muito bem naquilo. Né? Então, tem sim isso. Né? Explicando rapidinho como a gente funciona para a parte de motores, né? Da parte que você perguntou de IoT e a vibração mesmo. Então, a gente tem esse sensor que ele faz coletas da parte de vibração da máquina ali, e se a gente aplica ali uma transformada e etc., a gente consegue ver justamente as harmônicas e a parte de frequência ali do motor. Né? E todas as falhas que são categorizadas, que a gente tem um banco de dados de falhas muito grande, eles exibem ali naquele espectro uma forma diferente, né? Um desvio do funcionamento padrão que aquele motor deveria ter. Então, um passo também muito importante da nossa solução é o cliente entrar os dados daquela máquina, daquele motor específico, qual é a rotação, o que é aquilo que a gente está trabalhando, até qual tipo de rolamento, porque cada um vai ter um tipo de resposta e o problema vai dar harmônicos diferentes e etc. Né? E a parte de inteligência artificial, basicamente, todas essas coletas são analisadas, né, na cloud, na AWS, da vida, onde todas as coletas são analisadas a partir de um determinado treinamento da máquina, que é o funcionamento padrão dela. Né? Então, a gente utiliza sempre, toda vez que uma coleta sai de um sensor, passa por um receptor e vai para a internet, ela é processada, tanto ela quanto algumas passadas ali, né, para identificar justamente esse tipo de padrão. Né? Isso que a inteligência artificial é boa, a identificação de padrões ali, você identifica e bate esse padrão que a máquina está funcionando assim, mas tem mais uns 3, 4, 5 harmônicos aqui que são muito característicos de falha de rolamento. E a gente tem caracterizado uma falha de rolamento e a gente consegue pegar isso em pouquíssimo tempo, sabe? Se a máquina, que era para ter geralmente um pico ali perto do funcionamento dela, da rotação ali, talvez 1.700 RPM, 1.800 RPM, algo assim, ela começa a ter vários picos diferentes e várias coisas, vários harmônicos em frequências diferentes também, pode ser um desbalanceamento. A máquina pode ter só soltado o parafuso ali do chão. E a gente já pegou falhas desse tipo em motores que são mais ou menos do tamanho dessa mesa aqui, assim, né? E motores que vibram bastante e que geram esse tipo de problema, que é um problema assim, não, era no pé de um dos motores, né? Então, esse tipo de problema, o cara às vezes está fazendo uma inspeção, ele não vê, e com o sensor toda hora ali, postando essas coletas e sendo analisado por inteligência artificial ali atrás, ele realmente consegue identificar essa mudança de padrões aí e realmente descobrir essa falha. E o que a gente mais importa é avisar com antecedência que está acontecendo para o usuário, para que ele consiga interceder quando ele quer e não quando a máquina quer.
Olá, tudo bem?
Opa, bem.
Primeiro, no processo, todos os meus exemplos foram em cima de sensor de vibração e temperatura. Eu queria saber que outros produtos vocês têm. E segunda pergunta, como você devolve isso para o cliente? Você tem um relatório, você tem um sistema, você tem um aplicativo para gerar uma atenção melhor?
Sim, eu vi que não passou muito bem aqui, era para eu trazer um pouco mais disso, mas a gente tem uma plataforma online que pode ser acessada, né, tanto um aplicativo quanto pelo site mesmo. Então, tem lá um app.traction.com, onde o cliente vê todas as máquinas. Então, a gente tem um painel legal ali com todas as máquinas ao vivo mesmo, né, o que chegou ali para o cliente naquele momento. Então, a gente marca lá verdinho, essa máquina está funcionando. Se gera um alerta, ele recebe essa notificação no WhatsApp, no aplicativo, SMS, a gente avisa ele de várias formas que ele quiser, né? A gente consegue avisar de várias maneiras diferentes o que está acontecendo ali, e isso é marcado como um insight na plataforma. Então, o cliente vai acessar o site, vai abrir o aplicativo e vai ver que tem um insight, não, algo que ele precisa checar ali. Se ele checa e realmente tem aquele problema, já ajuda na pergunta dela que a inteligência artificial a gente consegue marcar que aquilo ali era realmente certo. Então, a gente está retroalimentando e falando, ó, isso aqui foi assertivo. Então, o modelo melhora um pouco mais e a gente consegue aprender justamente com esse feedback do cliente que ele dá na plataforma, no aplicativo e etc. Também você consegue verificar ao longo do tempo ali toda a parte das coletas, temperatura, vibração. Então, o cliente, até se ele tiver um conhecimento maior sobre a parte de vibração, ele consegue também clicar e falar, opa, mas eu vi uma coisa aqui. Então, até se a inteligência artificial não pegar, o cliente pode flaguear ali, né, marcar aquela parte como um desbalanceamento ou algo assim, algo estranho que ele viu, e aí a gente consegue, assim, melhorar o problema, né? Então, melhorar a IA em si para pegar aquele problema de novo, né? E, por enquanto, a gente está com 2 produtos, né? Esse produto que é teoricamente são 3, eu falei uma mensagem, mas um é só uma outra versão desse mesmo produto, né? A gente tem o Smart Track, que é o nosso produto de vibração e temperatura para as máquinas. Então, a gente, com ele, analisa máquinas que são rotativas, né? Máquinas que têm ali um motor que exercem determinada rotação e, por isso, vibram. A gente consegue analisar justamente por isso. E a gente também, agora tem um sensor de energia, que a gente liga ali nas fases de um trifásico ou a fase padrão ali na empresa, geralmente indústria é trifásica em tudo quanto é lugar, então a gente consegue ver tanto a tensão quanto a corrente ali do equipamento ou do painel. A gente consegue agora, com esse sensor de energia, detectar tanto desbalanceamento de rede ou problemas no equipamento que aquilo ali está sendo fornecida a energia. Né? Então, a gente consegue tanto instalar esse equipamento em uma subestação, por exemplo, ou se for um forno, que não faz, que não usa nenhuma parte rotativa ali, ele só tem um elemento resistivo, algo assim, a gente consegue ainda assim monitorar esse tipo de aplicação agora com esse produto da parte de energia. Né? E esse produto é o Energy Track, mas no Smart Tech a gente também tem a versão dele para zonas classificadas que a gente está começando a lançar agora, né? Porque a indústria também tem muita parte que é mais complicado de acessar e etc., né? Que são as zonas que são EX e etc., né? Que são zonas classificadas mesmo, e a gente não pode validar o mesmo sensor que a gente usa hoje para essas zonas, né? Então a gente teve que criar uma parte paralela ali do projeto justamente para ser um projeto certificável e que funcione nesse tipo de área que tem um requisito ali bem específico. Né? Nessas áreas tem gás, tem a parte de petróleo e gás também dentro da área X, a parte até às vezes de madeira também, tá? Porque a X não é só sobre gás, é sobre partículas também, né? Então a gente tem sim um produto diferente para esse tipo de aplicação. Então, hoje em dia são esses 3 tipos de produtos e tem mais algum tipo de produto que a gente está começando a explorar agora, mas aí vem no futuro e aí a gente deixa para uma próxima mesa.
Existe esse sensoramento das máquinas e tal, ele abre porta, né, para aplicação da ideia de aplicar agentes digitais, né, digital. Existe alguma perspectiva da empresa de fazer algum tipo de aplicação nesse sentido?
Não, fica desse lado.
Bom, pessoal, quem tiver mais perguntas, eu acho que o João Pedro vai ficar feliz de responder. Após a gente precisa prosseguir aqui para a próxima etapa do nosso evento. Obrigado, João Pedro, mais uma vez.
Valeu, gente. Obrigado.